Welcome back, sleepy learner. Tonight, we're going to drift through the science of airplanes, those remarkable machines that somehow learn to float on invisible rivers of air, carrying us across oceans and continents while we sip coffee and watch clouds drift past our windows. If you enjoy these gentle journeys through science, consider subscribing to the channel. It helps us keep creating these peaceful explorations of the world around us. Now, let's begin. Maybe you've seen old photographs of the Wright brothers, those two bicycle mechanics standing beside their fragile-looking contraption on the windswept beaches of Kitty Hawk. What's easy to forget when we think about that pivotal moment in 1903 is just how brief it actually was. The Wright brothers' first flight, the one that changed human history forever, lasted just 12 seconds. Yes, 12 seconds. Count them out slowly in your head, and you'll realize it's barely enough time to take a deep breath and let it out again. In those 12 seconds, their airplane covered only 120 feet. That's shorter than the wingspan of a modern Boeing 747. Think about that for a moment. The distance that represented humanity's first powered flight is now dwarfed by just one wing of our largest passenger aircraft. In little more than a century, a blink of an eye in human history, we went from that brief hop above the sand to planes that can stay airborne for 20 hours straight, crossing entire oceans without touching down. It's as if we learned to walk, and then, in the same afternoon, ran a marathon. The speed of that transformation is almost dizzying when you really consider it. But perhaps what's most beautiful about this fact isn't the contrast between then and now. It's that those 12 seconds were enough. Enough to prove it could be done. Enough to show that the dream of flight wasn't just a dream. Sometimes the smallest moments contain the seeds of the largest changes, and on that cold December morning in North Carolina, 12 seconds was all it took to reshape the future of human civilization. Every flight you've ever taken, every journey across the sky, traces its lineage back to those 12 fleeting seconds when two brothers showed the world that the impossible was simply the not yet accomplished. Here's something that might surprise you the next time you're seated by a window, watching the wings stretch out beside you as the plane climbs into the sky. Those wings aren't meant to be rigid. They're designed to bend, to flex, to move with the air rather than against it. A Boeing 787's wings, for instance, can flex upward by as much as 26 feet during flight. 26 feet, that's taller than a two-story house. Imagine the wingtip rising and falling by that distance, bending like a dancer's arm, responding to every current and thermal in the atmosphere. It seems counterintuitive, doesn't it? We think of aircraft as needing to be strong, and we associate strength with rigidity, with things that don't bend or break. But nature teaches us a different lesson. Think of a tree in a storm. The oak that stands rigid might snap, while the willow that bends survives. Airplane wings follow the willow's wisdom. This flexibility isn't a weakness, it's actually what makes them stronger. By allowing the wings to bend and absorb the forces of turbulence, the design prevents the kind of stress concentration that would occur in a rigid structure. The wing moves with the air, dancing with it rather than fighting it. There's something almost alive about this, isn't there? The idea that these metal structures breathe and flex, that they're engaged in a constant conversation with the wind. Every bump of turbulence, every gust from a thunderstorm, every thermal current rising from the earth below, the wing responds to all of it, bending and flexing in ways that are perfectly calculated yet somehow organic. It's a reminder that great engineering often means working with forces rather than against them, finding harmony and flexibility rather than stubborn resistance. The next time you fly, watch the wing. Watch it move. It's doing exactly what it was designed to do. Bending so it doesn't break, flowing so it can stay strong. If you've ever sat by an airplane window and looked closely, really closely at the glass, you might have noticed something curious. There's a tiny hole, usually near the bottom of the inner pane, barely large enough to fit the tip of a pen through. At first glance, it looks like a manufacturing defect, some mistake that slipped through quality control. But that little hole is there on purpose. It's called a breather hole, and it has a job to do, a quiet, invisible job that's absolutely essential to keeping you safe. Here's why it matters. Airplane windows aren't just one pane of glass, they're actually 3 layers working together. There's an outer pane that faces the hostile environment outside, the freezing temperatures, the thin air, the tremendous pressure difference between the cabin and the atmosphere at cruising altitude. There's a middle pane, and then there's the inner pane that you can touch and lean against. That little breather hole connects the space between the middle and inner panes to the cabin, allowing air pressure to equalize gradually. Without that hole, the pressure difference would build up between the layers, and the inner pane would have to bear part of the structural load. But with the breather hole doing its job, all the pressure stress falls on the outer pane, the one specifically designed and strengthened to handle it. The inner pane becomes, in a sense, just a passenger, along for the ride, protected from the forces that could shatter it. It's such a simple solution, really. A tiny hole, barely visible, performing a crucial function that most passengers will never notice or think about. And maybe that's what makes it beautiful, the idea that our safety often depends on small, quiet things working perfectly in the background. Not everything important announces itself. Sometimes the most critical elements are the ones we overlook, the little holes and hidden mechanisms that keep complex systems running smoothly while we sip our drinks and read our books, 35,000 feet above the earth. Lightning is one of nature's most dramatic displays of power, a violent discharge of electricity that can heat the air around it to temperatures 5 times hotter than the surface of the sun. So it might feel unsettling to learn that commercial airplanes are struck by lightning about once per year on average. That means if you fly regularly, the plane you're on has probably been hit by lightning at some point, maybe even recently. And yet, you've probably never noticed when it happened. You might have seen a flash, felt nothing more than a slight jolt, heard perhaps a distant rumble, but the plane kept flying, the lights stayed on, and everyone arrived safely at their destination. This isn't luck, it's physics, and it's beautiful physics at that. The aluminum fuselage of an airplane acts as what's called a Faraday cage. When lightning strikes the aircraft, the electrical charge flows around the outside of the metal skin, seeking the path of least resistance, but never entering the cabin or damaging the systems inside. It's the same principle that keeps you safe in a car during a lightning storm. The metal shell conducts the electricity around you, not through you. The charge enters at one point. Usually the nose or the wingtip travels along the exterior surface and exits at another point, often the tail. The whole event is over in a fraction of a second. Think about what that means. We've built these machines that can be struck by one of nature's most powerful forces and simply carry on. The passengers inside might not even know it happened. The pilots make a note of it in the log. Ground crews inspect the aircraft later for any minor damage to the exterior. but the flight continues as if nothing occurred. There's something reassuring about that, isn't there? The idea that we've learned to build protective shells around ourselves that can withstand even lightning strikes. We're fragile creatures travelling through a sometimes violent atmosphere. Yeah, but we've figured out how to move through it safely, wrapped in metal that knows how to let danger flow right past us, leaving us untouched in our pressurized bubble in the sky. Let's talk about something you probably don't think about much. Airplane tires. They seem so ordinary, so mundane compared to the miracle of flight itself. But if you look closer, they're actually small marvels of engineering. These tires are inflated to about 200 psi. That's roughly 6 times the pressure in your car tires. They need to be, because they're supporting weights that seem almost impossible. A single tire on a Boeing 777, for instance, can support up to 38 tons. That's the weight of about 25 cars, all resting on a circle of rubber smaller than a kitchen table. But the pressure and weight capacity are just the beginning. These tires need to survive the violent impact of landing. When a fully loaded jumbo jet touches down on a runway, its tires go from 0 to over 170 miles per hour in an instant. The moment the spinning wheels make contact with the ground, friction and the tire's rotation bring them up to speed almost instantly. That impact, repeated landing after landing, would destroy ordinary tires in minutes. Airplane tires are designed to handle it more than 500 times before they need replacement. 500 landings, each one a controlled collision with the Earth, each one generating tremendous heat and stress. And there's something worth pausing on here, something almost philosophical. These tires are a perfect example of how we build reliability into our most critical systems. They're over-engineered not because anyone expects them to fail, but precisely so they won't. They're designed with margins of safety built into every specification, every material choice, every structural element. When you're landing in a 300-ton aircraft travelling at highway speeds, there's no room for good enough. The tires don't just need to work, they need to work flawlessly, predictably, every single time. So the next time you're on a plane and you feel that gentle thump as the wheels touch the runway, think about those tires. Think about the pressures they're withstanding, the loads they're carrying, the engineering brilliance contained in something so seemingly simple. They're holding up hundreds of people and tons of metal and fuel, absorbing an impact that would pulverize almost anything else, and doing it all so smoothly that we barely notice. It's quiet heroism, written in rubber and pressure and carefully calculated stress limits. Look up on a clear day when a plane passes overhead, and you might see it trailing a long white line across the blue sky. A perfectly straight cloud that seems to follow the aircraft like a wake behind a boat. Most people call these contrails, short for condensation trails, and there's a common misconception that they're smoke pouring from the engines, some kind of pollution or exhaust. But they're not smoke at all. They're ice crystals, millions upon millions of tiny frozen water droplets suspended in the air, each one catching the sunlight, together forming that brilliant white line that can stretch for miles behind the plane. Here's how it happens. Jet engines burn fuel, and one of the byproducts of that combustion is water vapor, the same H2O that rises from a boiling kettle, just produced at a much larger scale and at extremely high temperatures. When this hot, moisture-laden exhaust meets the frigid air at cruising altitude, where temperatures can drop to 70 degrees below 0 Fahrenheit, the water vapor condenses instantly and then freezes, creating millions of ice crystals. It's the same process that makes your breath visible on a cold winter morning, just happening at 35,000 feet in air so cold and thin it's almost like space. But here's the interesting part. Contrails don't always appear. You need specific conditions. The air has to be cold enough and humid enough for those ice crystals to form and persist. If the air is too dry or too warm, the water vapor simply disperses invisibly into the atmosphere. This is why some days the sky is crisscrossed with contrails, and other days planes pass overhead leaving nothing behind. The plane is always producing that water vapor, but nature decides whether it becomes visible or stays hidden. There's something quietly beautiful about contrails if you stop to think about them. They're temporary drawings on the sky, geometric lines imposed on the chaos of clouds and weather. Some persist for hours, spreading out and eventually becoming part of the cloud layer themselves. Others vanish within seconds of forming. They're reminders of our passage through the upper atmosphere, breadcrumb trails showing where we've been. I'm visible proof that humans have learned to move through spaces that would kill us in seconds without our metal shells and carefully controlled environments. The next time you see one, maybe pause for a moment. Someone is up there, maybe reading a book or sleeping or looking down at the landscape below, leaving a temporary mark on the sky that will be gone by tomorrow. Here's a detail about air travel that sounds almost absurd until you think about it, and then it becomes perfectly reasonable, even essential. Pilots and co-pilots on commercial flights are required to eat different meals. It's an actual regulation. While you're in the back choosing between the chicken and the pasta, the two people responsible for flying the plane are sitting in the cockpit with different trays in front of them, one eating the chicken, the other eating the pasta, deliberately avoiding the same food. The reason is simple and slightly unsettling. Food poisoning. If both pilots ate the same meal and that meal happened to be contaminated with bacteria, Salmonella, E. coli, whatever pathogen decided to hitch a ride, both pilots could become ill at the same time. And while modern airplanes can practically fly themselves with their sophisticated autopilot systems, you still need conscious, functioning humans to make critical decisions, especially during takeoff, landing, and emergencies. The thought of both pilots incapacitated over the Atlantic Ocean is the stuff of disaster movies, so aviation authorities made sure it would never happen by enforcing this simple rule. Don't eat the same thing. It's such a mundane solution to a potentially catastrophic problem. No complex technology, no expensive equipment, just a policy that says, eat different meals. And yet this simple protocol has probably prevented more emergencies than we'll ever know about, because we don't hear about the near misses, the times when one meal was indeed contaminated, but only one pilot got sick while the other took over. We only hear about things when they go wrong, not when invisible safety measures work exactly as designed. There's a broader lesson hidden in this fact. Something about how we build reliable systems. It's not always about the dramatic interventions or the cutting-edge technology. Sometimes it's about thinking through the boring scenarios, the unglamorous possibilities, and putting simple redundancies in place. Two pilots eating different meals. It's almost comically simple. But it's also a small example of the thousands of tiny safety measures woven into every flight. Invisible threads in a safety net we never notice until we stop to look at how carefully it's been constructed. If you think about commercial aviation, you probably picture long flights, hours spent crossing oceans or continents, watching movies, trying to sleep in uncomfortable seats, counting down the time until landing. But there's a flight in Scotland that turns all of that upside down. It's the world's shortest scheduled commercial flight, connecting two small islands called Westray and Papay Westray in the Orkney Archipelago, far north of the Scottish mainland. The flight covers exactly 1.7 miles, and it lasts on average 90 seconds. 90 seconds. That's barely enough time to reach altitude. Except this flight doesn't really reach altitude at all. The plane climbs to maybe 500 feet, levels off briefly, and then immediately begins its descent. The pilot doesn't even retract the landing gear. There's no beverage service, no safety demonstration beyond the basics, no time to even unbuckle your seatbelt before you need to buckle it again. With favourable winds, the journey can take less than a minute. You could sneeze and miss a significant portion of the flight. It raises an interesting question. At what point does flying stop being about the destination and become simply the fastest way to get from one place to another? For the residents of these islands, this 90-second flight replaces what would be a 25-minute ferry ride, weather permitting. In the harsh North Atlantic, where storms can cancel ferries for days at a time, that little airplane becomes a lifeline. It carries mail, medical supplies, residents who need to reach the mainland for appointments or supplies. It's commercial aviation stripped down to its purest function, moving people and things through the air because it's the most practical option available. And maybe there's something charming about it too. In an age where we've normalised the absurdity of eating breakfast in one continent and dinner in another, where we think nothing of spending half a day in an aluminum tube crossing an ocean, there's something almost quaint about a 90-second flight. It reminds us that aviation isn't just about the spectacular or the extreme. It's also about the simple utility of moving through the air, whether you're travelling 9,000 miles or 1.7. Or the physics don't care about the distance. The miracle of flight works just as well for 90 seconds as it does for 18 hours. Here's a fact that might genuinely surprise you. Airplane black boxes aren't black, they're bright orange. Specifically, a highly visible shade of international orange that's designed to stand out against any background, whether it's ocean water, forest debris, or the twisted metal of a crash site. The nickname black box is so deeply embedded in our language that everyone uses it, even though it's been inaccurate for decades. So where did the name come from? There are a few theories. Some say it comes from the earliest versions of flight data recorders, which actually were housed in black boxes. Others suggest it refers to the charred, the blackened appearance these recorders often have after surviving the intense heat of a crash. Though they're built to withstand temperatures of over 1,000 degrees Celsius and impacts of thousands of Gs, the exterior can still show the scars of the disaster they've survived. Still others think it's simply because the data inside is opaque to the casual observer. You can't just open it up and read what happened. You need specialized equipment and expertise to decode the information locked inside. But whatever the origin of the name, the bright orange color serves a critical purpose. These devices hold the answers to what happened in those final moments before a crash. They record cockpit conversations, pilot inputs, system warnings, altitude changes, speed fluctuations, hundreds of parameters captured moment by moment, me creating a detailed record of the flight. After an accident, investigators need to find these recorders, often searching through vast areas of wreckage or debris fields. The orange colour, combined with reflective tape and an underwater locator beacon that can ping for 30 days, gives searchers the best possible chance of recovering these vital pieces of evidence. It's worth pausing on what these devices represent. They're designed to survive the unsurvivable, to remain intact when everything around them has been destroyed. They're built to witness catastrophe and preserve the memory of it, creating a record that can help prevent future disasters. There's something almost sacred about that purpose, isn't there? These orange boxes are memory keepers, truth tellers, the last testimony of what went wrong so that we can learn and improve. And despite the grim circumstances that make them necessary, they've made flying safer by orders of magnitude. Every lesson learned from a recovered black box, orange box really, has been written into new regulations, better training, improved designs. They're painted bright orange so they can be found. But they're built to survive so the truth can never be lost. Try to imagine 6 million of anything. 6 million grains of sand, 6 million seconds, 6 million steps. It's a number so large it becomes almost abstract, difficult to hold in your mind as something concrete and countable. And yet, a typical commercial airplane contains more than 6 million parts. 6 million separate components, each one designed, manufactured, tested and assembled with precision. There are over 75 miles of electrical wiring running through the fuselage. If you unspooled it all and laid it in a straight line, it would stretch from one end of a small city to the other. Think about what that means. Every single one of those 6 million parts has to work correctly, has to be properly installed, has to interact with thousands of other parts exactly as designed. The complexity is staggering, and yet, somehow, these machines achieve reliability rates that would seem impossible for something so intricate. But here's the unsettling part. If just one critical bolt, a single piece of metal the size of your fingernail, one tiny component among 6 million, if that one bolt fails at the wrong moment, the entire aircraft could be compromised. This is why aviation maintenance is so meticulous, so obsessively careful. Mechanics don't just check the big obvious things, they inspect individual bolts, looking for hairline cracks, corrosion, anything that might indicate stress or wear. They follow maintenance schedules measured in flight hours, calendar days, and number of cycles. A cycle in aviation terms is one complete flight, from takeoff to landing, because the pressurization and depressurization of the cabin, the stress of acceleration and deceleration, all of that creates wear that accumulates over time. Parts are replaced not when they fail, but long before they're expected to fail, building in margins of safety upon margins of safety. And perhaps what's most remarkable is that this system works. Despite the complexity, despite the 6 million potential points of failure, commercial aviation has become the safest form of long-distance travel humans have ever devised. Statistically, you're safer in an airplane than you are driving to the airport. That safety doesn't come from simplicity. It comes from carefully managed complexity. From understanding that 6 million parts means 6 million things to check, to monitor, to maintain. It comes from respecting the fact that something as seemingly insignificant as a fingernail-sized bolt can matter immensely, and treating every component with the seriousness it deserves. 6 million parts, all working together, keeping hundreds of people safe as they fly through the sky. It's an achievement we should pause to appreciate more often than we do. There's a specific altitude where most commercial flights spend the majority of their time, around 35,000 feet, though it can range from 30,000 to 42,000 depending on the aircraft, the route, and the winds. If you've ever wondered why planes fly so high, why they don't just cruise along at 10 or 15,000 feet, where the air is thicker and easier to breathe, The answer is a beautiful example of finding the sweet spot between competing forces. At 35,000 feet, the air is incredibly thin, only about a quarter as dense as the air at sea level. This thinness is actually an advantage. Thinner air means less drag, less resistance pushing against the aircraft as it moves forward. It's like the difference between walking through waist-deep water and walking on dry land. The plane can move much more efficiently through that thin air. The engines don't have to work as hard to maintain speed, which means they burn less fuel. And when you're moving hundreds of tons of metal across continents, fuel efficiency matters enormously. A few percentage points of improvement can translate to millions of dollars saved and significantly reduced emissions, but you can't fly too high. Eventually the air becomes so thin that the engines can't get enough oxygen to burn fuel efficiently, and the wings can't generate enough lift to keep the plane aloft. There's ceiling, a maximum altitude that depends on the aircraft's weight, engine power and wing design. And so 35,000 feet represents a compromise, high enough to escape the drag of denser air, but not so high that the fundamental physics of flight stop working in your favour. There's another benefit too, one that passengers appreciate even if they don't always realise it. At this altitude, you're above most weather systems. Those towering thunderstorms that can make flights turbulent and uncomfortable rarely reach above 30,000 feet. Up here, the air is often smooth, stable, almost serene. You're flying in the stratosphere, a layer of the atmosphere where temperature actually increases with altitude instead of decreasing, creating a stable environment without the convective currents that cause turbulence below. It's a quieter realm, literally and figuratively. The roar of the jet engine sounds different up here. And the ride is smoother. So when you're cruising at 35,000 feet, reading a book or watching a movie, remember that you're positioned at a very specific point in the atmosphere, not too low, not too high, but right where the mathematics of flight and fuel efficiency and passenger comfort all align. It's another example of how flying is about finding balance, about working with the invisible forces of physics rather than against them. The air up here is thin and cold, and would kill you in minutes without the pressurized cabin protecting you. But it's also exactly where the plane is happiest, where it can glide most efficiently through the sky on its journey from one distant place to another. Let's talk about something that's simultaneously mundane and surprisingly impressive: airplane toilets. If you've ever used one, you've probably noticed that distinctive sound, a loud, rushing whoosh that seems disproportionately powerful for such a small space. There's a reason for that sound. Airplane toilets use a vacuum system that creates suction speeds of over 300 miles per hour. To put that in perspective, that's faster than most NASCAR races. The waste isn't just falling down a pipe under gravity, it's being actively sucked away by a partial vacuum at speeds that would make a race car driver envious. The engineering challenge here is interesting. At home, your toilet uses gravity and water, usually several gallons per flush, to carry waste down through plumbing to the sewer system. But on an airplane, you can't rely on gravity because the plane might be banking, climbing, descending, or even temporarily experiencing turbulence that creates negative g-forces. And you certainly can't use several gallons of water per flush when every pound of weight costs fuel and limits how many passengers or how much cargo you can carry. Water is heavy, 8 pounds per gallon, and if you multiplied that by hundreds of passengers over a long flight, you'd be carrying thousands of pounds of extra weight. So instead, airplane toilets use a brilliant alternative. When you press the flush button, A valve opens and air pressure does the work. The cabin is pressurized to about 8 psi higher than the outside air at cruising altitude, and when that valve opens, the pressure differential creates a powerful vacuum that sucks everything through the system at tremendous speed. The waste goes into a holding tank that's sealed and stored until the plane lands, at which point ground crews service it, a job that's unglamorous but absolutely essential to keeping the system working. That whooshing sound you hear isn't everything being ejected into the sky, despite what some people believe. That's an urban legend that refuses to die. Nothing leaves the aircraft in flight. It's all contained in those sealed tanks. The sound is simply air rushing to fill the vacuum, nature's way of evening out pressure differences. And maybe there's something oddly satisfying about that sound, knowing that even something as basic as an airplane toilet involves careful engineering, vacuum dynamics, and speeds that would seem absurd if you described them at a dinner party. 300 miles per hour in a bathroom, at 35,000 feet. Sometimes the most ordinary moments of our lives are more extraordinary than we realize. Here's something you might have noticed if you've ever taken an evening or night flight. As the plane prepares for takeoff or landing, the cabin lights dim. They don't go out completely, but they noticeably reduce, creating a softer, more subdued environment. Some passengers might assume it's for ambience, a way to help people relax or sleep. But the real reason is far more practical and, in a quiet way, quite serious. Those dimmed lights are preparing your eyes for darkness in case something goes wrong. The human eye needs time to adjust to changes in light level. Specifically, it takes about 30 seconds for your pupils to dilate fully when moving from bright light to darkness. That might not sound like much, but in an emergency evacuation, those 30 seconds could be the difference between being able to see the exit path markers on the floor or stumbling blindly through the cabin. Takeoff and landing are the most critical phases of flight, the times when the vast majority of accidents occur if they're going to occur at all, and if an accident happens at night, the interior of the cabin might suddenly be plunged into darkness. By dimming the cabin lights beforehand, the crew is giving your eyes a head start. If the lights go out completely, your pupils are already partially adjusted. You're not starting from zero, you're halfway there. Those illuminated exit signs, those floor-level emergency lighting strips, the glow of moonlight through the windows, all of that becomes visible much faster if you're not coming from full brightness. It's a small preparation, a just-in-case measure that hopefully will never be needed. But if it is needed, it could save lives. There's something quietly reassuring about this, isn't there? The idea that even the lighting levels in the cabin have been thought through, calculated, optimized for safety. Most passengers will never know why the lights dim. They'll assume it's a nice touch, maybe think the airline is trying to help them sleep. And in 99.9% of flights, that's effectively what it does. Creates a calmer environment for landing. But underneath that calming effect is a safety measure, one more layer of protection built into every flight. The crew isn't just setting a mood, they're preparing for the possibility of darkness, making sure that if the worst happens, your eyes will be ready to find the way out. It's care disguised as comfort, and maybe that's the best kind of safety measure, the kind you never notice until you need it. Imagine you're on a flight over the ocean, thousands of miles from the nearest airport, when suddenly one of the engines fails, just stops running. The sound changes, the vibration pattern shifts, and if you're paying attention, you might notice the plane seems to be flying slightly asymmetrically. It sounds like the beginning of a disaster movie. But here's the thing, it's not a disaster. In fact, it's a scenario that pilots train for extensively because modern jetliners are designed to fly, and fly safely, on just one engine. This isn't a theoretical capability or a last-ditch emergency measure. Commercial aircraft are certified before they're ever allowed to carry passengers, rest to maintain altitude, and even climb on just half their engines. A Boeing 777, for instance, can lose one of its two engines and continue flying for hours, covering hundreds of miles to reach an alternate airport. The FAA and other aviation authorities have a term for this, ETOPS, which originally stood for Extended Range Twin Engine Operational Performance Standards, though pilots jokingly call it engines turn or passengers swim. It's a certification that allows twin-engine aircraft to fly routes that might take them more than 60 minutes away from the nearest suitable airport. The engineering that makes this possible is remarkable. The remaining engine has to be powerful enough not just to keep the plane level, but to compensate for the asymmetric thrust, the fact that all the power is now coming from one side. The wing structure has to be strong enough to handle the uneven forces. The flight control systems have to be sophisticated enough to automatically adjust rudder and aileron positions to keep the plane flying straight. And all of this has to work reliably enough that regulatory authorities are comfortable with planes flying routes over vast stretches of ocean or empty wilderness where there are no nearby places to land. Think about what that means for a moment. When you're on a transatlantic or transpacific flight, the very fact that the flight is happening means the aircraft has been certified to complete the journey, even if half its engines fail. That's not just redundancy, it's extreme redundancy, built into the fundamental design. Pilots practice single-engine approaches and landings in simulators. They know the procedures by heart. And while engine failures are rare, modern jet engines are incredibly reliable. When they do happen, they're usually non-events from the passenger's perspective. The plane continues, perhaps diverting to a closer airport out of an abundance of caution, but continuing nonetheless. It's yet another example of how we've built safety into aviation at every level, preparing for failures before they happen, and ensuring that even when things go wrong, they don't have to go catastrophically wrong. There was an airplane called the Concorde that flew faster than the speed of sound, not just a little faster, but roughly twice as fast, cruising at Mach 2.04, which translates to about 1,354 miles per hour. At that speed, the Concorde could cross the Atlantic Ocean in under 3 hours, London to New York in 2 hours and 52 minutes. And because of the time zone difference between London and New York, 5 hours, passengers would arrive in New York before they departed London, at least according to the clocks on the wall. Imagine experiencing that. You board in London at 10:30 a.m. local time. You fly for nearly 3 hours, eating a meal, perhaps reading or working or simply watching the curvature of the earth become visible through the windows, because at 60,000 feet the sky above you appears dark blue, almost purple, and you can actually see the planet's curve. And then you land in New York at 9:25 a.m. local time. You've travelled backward in time, at least by the arbitrary convention of time zones. Passengers could literally watch the sun rise in the west as they outran Earth's rotation, racing westward faster than the planet could turn beneath them. Or the Concorde was a marvel, but it was also a compromise. Beautiful and fast, but phenomenally expensive to operate, incredibly loud, and so fuel-hungry that it could never be profitable in the modern era of aviation economics. It was retired in 2003 and since then, commercial supersonic flight has vanished from our skies. We've actually gotten slower in the decades since. The fastest way to cross the Atlantic now takes about 7 hours instead of 3. We chose efficiency and affordability over speed, practicality over prestige. But there's something wistful about the loss of the Concorde, isn't there? It represented a moment when we reached for something audacious, when we decided that merely flying wasn't enough. We wanted to fly faster than sound itself. For a few decades, it was possible to pay for a ticket and experience something that felt genuinely futuristic, to arrive at your destination before you left your origin, to outrun the sun across the sky. That era is gone now, and while there are companies working to bring back supersonic flight, it remains to be seen whether we'll ever return to that brief period when a handful of people could travel through time zones faster than time itself. The Concorde is grounded, a museum piece now, but the memory of what it could do still carries a certain magic, a reminder that sometimes, just sometimes, we reach for the impossible and actually grasp it, even if we can't hold on forever. Here's something that might seem strange at first. Airplane fuel isn't stored in tanks tucked away in the fuselage like you might imagine. Instead, and it's stored in the wings themselves. The wings are hollow structures carefully sealed and designed to hold thousands of gallons of jet fuel. A Boeing 747, for instance, can carry over 50,000 gallons of fuel, and the vast majority of it sits right there in the wings, sloshing gently back and forth as the plane maneuvers through the sky. At first, this seems like a choice made purely out of convenience. The wings are big, hollow spaces, so why not use them for storage? But there's actually a more elegant reason, one that reveals how deeply engineers think about every aspect of aircraft design. When you put weight in the wings, you're actually helping to reduce stress on the wing structure during flight. Let me explain. Wings generate lift, which means they're constantly being pushed upward by the air flowing over and under them. And this creates what's called bending stress. The wings want to bend upward at the tips like arms lifting a heavy weight. If the wings were empty, all of that lift force would have to be counteracted by the wing's internal structure, the spars and ribs that give it strength. But when you add fuel weight to the wings, you're creating a downward force that partially offsets the upward lift. The wing is still lifting the airplane, but it's also carrying its own load, and these forces balance each other in a way that actually reduces the peak stress on the wing structure. It's a beautiful example of engineering efficiency, using storage space not just as storage, but as structural support. The fuel isn't just along for the ride, it's actively contributing to the aircraft's structural integrity. And as the fuel burns during flight, the load decreases gradually, which is perfectly fine because the plane is also getting lighter overall, requiring less lift to stay airborne. Everything is connected, every choice affecting multiple systems at once. There's something almost poetic about this, isn't there? The fuel that powers the engines and keeps the plane flying is also helping to hold the wings together, reducing the stress on the very structure that makes flight possible. It's synergy at a fundamental level, multiple problems solved by a single solution. The next time you're on a plane, maybe glance out at the wing and remember that it's not just lifting you through the air, it's also carrying the fuel that makes the journey possible, and in carrying that fuel it's actually making its own job easier. Everything in balance, everything working together, the 35,000 feet above the earth. Take a deep breath right now, wherever you are. If you're on the ground, that breath contains air that's been filtered by trees and plants. mixed by wind, warmed or cooled by weather systems. Now imagine that same breath at 35,000 feet, inside an aluminum tube travelling at 500 miles per hour. The air you're breathing in an airplane cabin isn't quite the same as the air on the ground, and understanding where it comes from reveals another layer of the quiet complexity that keeps you alive in an environment that would kill you in seconds. About half the air in an airplane cabin is recycled. It's pulled from the cabin, passed through HEPA filters, the same high-efficiency particulate air filters used in hospitals and clean rooms, and then pumped back in. The other half is fresh air, but fresh is a relative term when you're 6 miles above the Earth. This air is pulled from outside the aircraft, from the atmosphere the plane is flying through. At that altitude, the air is far too thin to breathe. There simply aren't enough oxygen molecules per breath to keep you conscious. So the engines compress it, squeeze it until it is dense enough to sustain life, heat it to a comfortable temperature, and feed it into the cabin. Those HEPA filters do remarkable work. They remove more than 99.97% of airborne particles, including bacteria, viruses, and other contaminants. In many ways, the air in an airplane cabin is actually cleaner than the air in most office buildings or homes. It's completely exchanged, replaced with fresh air every 2 to 3 minutes. That's far more frequently than most buildings, where air might circulate only a few times per hour. So while the cabin might feel stuffy or dry, the air itself is being constantly renewed, constantly filtered. But here's the thing, the air is dry, extremely dry. The humidity in an airplane cabin is typically below 20%, which is drier than most deserts. The Sahara Desert on average has about 25% humidity. You're literally in a drier environment than one of the harshest deserts on Earth. This happens because the fresh air being pulled in from outside is compressed and heated, and that process removes moisture. Adding humidity back would require carrying additional water, which is heavy, and would also risk condensation forming inside the aircraft structure, which could lead to corrosion over time. So when your skin feels parched on a long flight, when your eyes feel dry and your throat scratchy, that's not your imagination. You're breathing clean, filtered air, but air that's been stripped of most of its moisture. It's another trade-off, another compromise between competing needs. Breathable air versus weight versus structural integrity versus passenger comfort. The system works, keeps hundreds of people alive in an environment that's hostile to human life, but it's not perfect. Nothing about flying is perfect. It's all about finding acceptable balances between impossible demands, and somehow, remarkably, those balances work well enough that we barely think about them as we read our books and sip our drinks, breathing recycled, filtered, desert-dry air while racing through the stratosphere. Let's talk about fuel consumption, because the numbers are almost absurd. A Boeing 747, one of the largest passenger aircraft in the world, uses about 1 gallon of fuel per second during cruise flight. 1 gallon every second. If you count out 60 seconds, imagine 60 milk jugs of jet fuel being consumed, burned, converted into heat and thrust, and the energy that keeps 300 tons of metal and people and cargo moving through the sky. Over the course of a long international flight, that 747 might burn through 50,000 gallons of fuel or more. At first, that sounds wasteful, almost grotesquely inefficient. 1 gallon per second. How could that possibly be sustainable or environmentally responsible? But here's where perspective matters, where you have to zoom out and look at the bigger picture. that 747 isn't carrying one person, it's carrying up to 500 people. When you divide that fuel consumption by the number of passengers, the math becomes surprisingly reasonable. 1 gallon per second, divided among 500 people, works out to roughly 100 miles per gallon per passenger. That's more fuel efficient than most cars on the highway. Think about that for a moment. You're travelling at 550 miles per hour, 6.5 miles above the Earth, and your share of the fuel consumption is comparable to, or even better than, driving the same distance alone in a car. The physics of flight becomes remarkably efficient when you're moving hundreds of people at once. It's the principle of scale, the same reason a full bus is more efficient than dozens of individual cars. But unlike a bus, this vehicle is defying gravity, compressing and heating air for you to breathe, protecting you from temperatures that would freeze you solid, all while moving faster than any car could ever dream of travelling. Of course, this doesn't mean flying has no environmental impact. Aviation contributes about 2 to 3% of global CO2 emissions, and there are other effects too. Contrails that trap heat, nitrogen oxides produced at high altitude, the cumulative impact of billions of passenger miles flown each year. These are real concerns, and the industry is working on solutions. More efficient engines, sustainable aviation fuels, better aerodynamics, even electric and hydrogen-powered aircraft in development. But it's worth acknowledging the achievement here. Yeah, the sheer efficiency that's been wrung out of these machines through decades of refinement. We've taken the audacious act of flight, of lifting hundreds of people into the sky and carrying them across continents, and made it surprisingly fuel efficient on a per-person basis. 1 gallon per second sounds like a lot, and in absolute terms it is. But divided among 500 people, travelling at speeds that would have seemed like magic a century ago, it's actually a testament to how far we've come in making the impossible not just possible, but practical. The numbers are large because the achievement is large. And maybe that's okay. There's a reason airplane windows are round, or more precisely, why they have rounded corners rather than sharp angles. It seems like a small detail, almost purely aesthetic, but it's actually one of the most important safety features on the aircraft. A lesson learned through tragedy and written into every airplane design since. In the early 1950s, the first commercial jetliners began entering service, and they were revolutionary. The de Havilland Comet, a British aircraft, was the first. Beautiful, fast, pressurized, able to fly higher and faster than any commercial plane before it. But within a couple of years, several Comets suffered catastrophic failures, breaking apart in mid-flight with no warning. The wreckage was scattered across the ocean. The loss of life was devastating, and nobody initially understood why. These were new planes, well-maintained, flown by experienced crews. What could possibly cause such sudden, violent failures? The investigation was painstaking. Engineers eventually recovered enough wreckage to reconstruct parts of the fuselage, and they discovered something crucial. The fractures had originated at the corners of the square windows. Every time the aircraft climbed to altitude and the cabin pressurized, stress concentrated at those sharp corners, the 90-degree angles where the window frame met the fuselage. Over time, with repeated pressurization cycles, microscopic cracks formed at those stress points. The cracks grew, slowly at first, then faster, and eventually the metal failed catastrophically, tearing the fuselage apart. The solution was elegantly simple. Round the corners, curves distribute stress evenly, unlike sharp angles where force concentrates. It's the same principle that explains why you can tear a piece of paper easily if you start with a small notch, but struggle to tear it along a smooth edge. Round windows spread the stress around the opening instead of focusing it at specific points. Every airplane since the Comet disasters has used round or oval windows with smoothly curved corners. It's a safety feature so fundamental that we don't even think about it anymore. But maybe we should think about it, just for a moment. Those rounded windows represent lives lost and lessons learned. A reminder that engineering isn't just about what works in theory, it's about what works under real-world conditions, through thousands of cycles of stress and strain. It's about learning from failures and making sure they never happen again. Every time you look out an airplane window at the clouds or the landscape below, you're looking through a shape that was refined by tragedy into something safer. Love, the curves are there for a reason, a quiet testament to the hard-won knowledge that makes modern flight possible. Here's a comparison that really puts the scale of modern aviation into perspective. The Boeing 747's horizontal stabilizer, that's the small wing-like structure at the tail of the aircraft, the one that helps keep the plane stable in pitch, has a larger wingspan than the entire Wright brothers' first airplane. Let that sink in for a moment. A component designed solely for stability, not even for generating lift, is bigger than the aircraft that first proved human flight was possible. The Wright Flyer had a wingspan of just over 40 feet. The 747's horizontal stabilizer spans more than 70 feet. A single tail component on a modern jetliner dwarfs the machine that started it all. It's a perfect illustration of how far we've come in barely more than a century. In 1903, the Wright brothers built a craft that could carry one person a few hundred feet. By 1970, we were building aircraft that could carry 500 people across oceans, with tail surfaces larger than that original plane. But the comparison isn't just about size, it's about purpose and specialization. The Wright Flyer was a complete aircraft, everything it needed to achieve powered flight distilled into a fragile framework of wood, fabric, and wire. The 747's horizontal stabilizer is just one small part of a vastly more complex system, each component refined and optimized for a specific function. That tail surface doesn't generate lift for flight, it provides pitch stability and control. It keeps the nose from pitching up or down unexpectedly. It's a specialist doing one job extremely well as part of a larger team of components, and there's something both humbling and inspiring about this progression. The Wright brothers would have been astounded by a 747, probably unable to fully comprehend the engineering that makes it possible. Yet their achievement was the seed from which all of this grew. Every principle they discovered, every problem they solved about control surfaces and propulsion and wing design. Those insights cascaded forward through generations of engineers and inventors, each one building on what came before, adding complexity and capability and scale. So when you see a 747, or any modern airliner really, maybe take a moment to appreciate not just its size, but what it represents. A century of continuous refinement, of problems solved and lessons learned, of ambitions that grew from can we fly at all, to can we carry hundreds of people safely across the world. The horizontal stabilizer is bigger than the Wright Flyer, and somehow that feels exactly right. A small part of today's achievement dwarfing yesterday's entire dream. Here's a fact that might make you think twice about where you eat your in-flight meal. Airplane tray tables are among the dirtiest surfaces in the entire cabin. Studies have found that they often harbour more bacteria than the toilet flush button, sometimes significantly more. We're talking about surfaces that can have 8 times the bacterial count of the lavatory, places where E. coli, MRSA, and various other microorganisms have been detected in concerning quantities. The reason is almost embarrassingly simple: cleaning schedules. Between flights, these cleaning crews have limited time, sometimes as little as 15 or 20 minutes, to prepare the aircraft for the next group of passengers. In that brief window, they're focused on removing visible trash, restocking supplies, and tidying the cabin. The toilets get cleaned and sanitized because that's a priority both for appearance and hygiene. But tray tables, they might get a quick wipe down if they're visibly soiled, but often they're simply folded back up and left as is. And those tray tables see a lot of use. They're surfaces for food and drinks, yes, but passengers also use them for everything else you can imagine. People change diapers on them. This actually happens more often than you'd think. They rest their bare feet on them. They sneeze and cough toward them. They spill things, leave sticky residues. They deposit skin cells and oils and whatever else was on their hands. All of that accumulates, and unless someone specifically sanitizes the surface, it stays there, waiting for the next passenger who unfolds that tray to eat their meal. Now, before this triggers too much anxiety, it's worth noting that most people survive these encounters just fine. Our immune systems are remarkably good at dealing with everyday bacteria, and the actual risk of getting sick from a tray table is probably quite low. But it's still a good reminder that airplane cabins, for all their engineering sophistication, are ultimately shared spaces that hundreds of people cycle through each day. They're not sterile environments, they're more like flying buses or subway cars, functional, reasonably safe, but not necessarily pristine. The solution, if this bothers you, is simple. Carry disinfectant wipes and give your tray table a quick wipe down before you use it. Many frequent travellers do exactly this. It takes 10 seconds and provides peace of mind. Or don't eat directly off the surface, use a napkin, or keep your food in its packaging. Small precautions for a small risk, but sometimes knowing about these hidden dirty spots makes us more mindful about the spaces we inhabit and share. The tray table folds down the same as always, ready to serve its purpose, whether it's been cleaned or not. What you do with that information is up to you. The Airbus A380 is a study in superlatives, the largest passenger airliner ever built, a double-decker giant that seems to defy common sense about what should be able to fly. When you see one parked at an airport, it dominates the terminal, making other large aircraft look almost modest by comparison. The numbers are almost absurd. It can carry over 800 passengers in a high-density configuration, though most airlines configure it for around 500 to 600. The wings are nearly as large as a basketball court. If you could somehow flatten them out and paint court lines on them, you could play a regulation game. And yet, despite weighing 1.2 million pounds at maximum takeoff weight, this massive machine can still lift off the ground in under 10,000 feet of runway. Think about that. 1,200,000 pounds. The equivalent of 600 cars, or 100 elephants, or just an incomprehensibly massive amount of weight, rolling down a runway, accelerating, and then simply rising into the air because the wings are generating enough lift to overcome gravity. The physics is well understood, but the reality still feels magical when you witness it. The A380 was designed to solve a specific problem: airport congestion. If you can't add more flights because runways and gates are at capacity, make the existing flights bigger. pack more people into each takeoff and landing slot. It made sense on paper, and the aircraft itself is an engineering triumph. But the economics proved challenging. Airlines discovered they'd rather fly two smaller planes on different schedules than one giant plane once a day. Flexibility mattered more than capacity. The A380 never sold in the numbers Airbus hoped for, and production ended in 2021. But there's something magnificent about the A380 regardless of its commercial challenges. It represents the far edge of what's possible with current technology, the biggest passenger aircraft we could build with the materials and engines and aerodynamics we have available. It's a monument to ambition, a flying testament to the question, how big can we go? And the answer, apparently, is this big. Wings the size of a basketball court, weight measured in millions of pounds, capacity for hundreds of passengers spread across 2 full decks. When you see an A380 take off, there's a moment where it seems impossible, where your brain insists that something that large and heavy shouldn't be able to float. But it does. It rises smoothly, almost gracefully despite its bulk, and climbs into the sky like it belongs there. And maybe that's the real achievement. Not just that we could build something this large, but that we could make it fly with the same fundamental principles that lift a small Cessna. Scale changes everything and nothing. The physics doesn't care about size. Lift is lift, thrust is thrust, and if you generate enough of both, even a basketball court-winged giant can dance among the clouds. Imagine this scenario. A commercial airliner is approaching its destination when an emergency situation develops, medical, mechanical, whatever the reason, and the plane needs to land immediately. But there's a problem. The aircraft is still heavy with fuel, loaded up for a long journey, and it's too heavy to land safely. The landing gear and wing structure are designed to handle the impact of landing, but only up to a certain weight. Exceed that weight, and you risk damaging the aircraft or even causing the landing gear to collapse. So what do? Sometimes the answer is to dump fuel. The pilot flies the aircraft to a designated area, usually over water or unpopulated land, and releases thousands of gallons of jet fuel into the atmosphere. Special valves open on the wings, and the fuel streams out, creating visible trails behind the aircraft. It sounds almost scandalously wasteful, not to mention environmentally concerning. But it's a carefully regulated emergency procedure used only when necessary, when the risk of landing overweight exceeds the cost of dumping the fuel. Here's what happens to that fuel. It doesn't fall to the ground as liquid. As it streams out of the aircraft at high altitude, it atomizes, breaks apart into tiny droplets, and then evaporates into a fine mist. By the time it would reach the ground, it's dispersed so thoroughly into the atmosphere that it's essentially gone, diluted beyond any meaningful concentration. The evaporation happens quickly in the cold, dry air of high altitude, and the resulting vapor mixes with millions of cubic feet of air, spreading out over vast areas. Now, not all aircraft can dump fuel. Smaller planes and some medium-sized aircraft don't have the capability. They have to either burn off fuel by flying in circles, which can take a long time, or accept the risk of an overweight landing if the situation is serious enough. But large, long-range aircraft like the Boeing 747 or 777 have fuel dump systems precisely because they might need to land shortly after takeoff, when they're still carrying thousands of gallons meant for a flight halfway around the world. There's something sobering about this capability. It's a reminder that even in our highly engineered systems, sometimes the solution to a problem is simply to jettison what you don't need, to sacrifice resources for safety. That fuel cost tens of thousands of dollars, took energy to produce and transport, represents environmental impact, but in an emergency, none of that matters compared to getting the aircraft and its passengers safely on the ground. So the fuel streams out, evaporates, disperses into the atmosphere like it was never there, and the plane becomes light enough to land. It's a solution that feels wasteful and elegant at the same time. Wasteful in resources, elegant in how completely it solves the immediate problem. Modern commercial aircraft are equipped with autopilot systems so sophisticated that they can handle virtually every phase of flight. Takeoff, climb, cruise, descent, approach, even landing. All of it can be automated. The technology exists for the plane to fly itself from the moment it leaves the gate to the moment it arrives at the destination gate, with minimal human input. In fact, some pilots have completed entire transoceanic flights, touching the controls for less than 7 minutes total, just enough to taxi, configure the autopilot, monitor the systems, and then taxi again at the destination. This might sound unsettling at first. You're trusting your life to a computer? But the reality is that these autopilot systems are extraordinarily reliable, far more consistent than human pilots in many routine situations. They don't get tired. They don't get distracted. They don't have bad days or emotional responses to stress. They fly the programmed route with precision measured in feet and seconds, making thousands of tiny adjustments per minute to keep the aircraft exactly on course, at exactly the right altitude and speed. And yet, despite this capability, regulations require that human pilots remain in control, monitoring the systems, ready to intervene if something goes wrong. The autopilot is a tool, not a replacement. Pilots program it, supervise it, and can disconnect it instantly if needed. During critical phases like takeoff and landing, even though the autopilot could theoretically handle everything, many airlines require pilots to fly manually, or at least have their hands near the controls ready to take over. The automation is there to reduce workload during the routine parts of flight, allowing pilots to focus on monitoring systems, communicating with air traffic control, planning for contingencies. There's a philosophical question hidden in all of this. At what point does a human become a supervisor of machines rather than an operator? And is that a good thing or a concerning thing? Airlines argue that automation has made flying safer by reducing human error, which is responsible for the majority of aviation accidents. The autopilot doesn't make the kinds of mistakes that humans make, forgetting a checklist item, misreading an instrument, making a poor decision under stress. But critics worry about skills atrophy, about pilots who spend so much time monitoring automation that they struggle when they suddenly need to fly manually in an unexpected situation. The truth is probably somewhere in the middle. Automation's a powerful tool that has made commercial aviation incredibly safe and efficient. But it's still just a tool, dependent on human oversight, human decision-making, human intervention when the unexpected occurs. The autopilot can fly the plane for hours, executing a perfect flight plan. But it's the human pilot who understands why the flight plan makes sense, who can recognize when something isn't right even if all the systems show normal readings, who can improvise when confronted with the situation the programmers never anticipated. 7 minutes of actual control time over a 12-hour flight might sound like the humans are barely involved, but those 7 minutes, and the monitoring in between, are what keep the sophisticated automation working exactly as intended. It's a partnership, whether we think of it that way or not. Here's a testing procedure that sounds almost comical until you realise how serious it is. Airplane engines are tested by launching frozen chickens into them at high speed. Real chickens, or at least chicken carcasses, shot from a specialised cannon directly into a running jet engine at velocities simulating what would happen if a bird struck the engine during flight. The term for this is chicken gun testing, and it's a crucial part of the certification process for any new aircraft engine. The reason is straightforward. Bird strikes happen. They're relatively common, especially during takeoff and landing when aircraft are at lower altitudes where birds fly. A bird weighing just 4 pounds hitting an engine that's spinning at thousands of RPM and ingesting hundreds of pounds of air per second can cause catastrophic damage if the engine isn't designed to handle it. Blades can break, fragments can pierce the engine casing, the whole turbine can fail in a spectacular and dangerous way. So regulators require that engines prove they can survive these impacts. The test is deliberately harsh. A 4-pound chicken, frozen solid to simulate the worst-case impact characteristics, launched at the engine while it's running at full power. The engine has to keep running after the strike, or at least it has to fail in a controlled way that doesn't endanger the aircraft. Ideally, the engine ingests the bird, chews it up and continues operating, perhaps with some damage that requires eventual repair, but not a catastrophic failure that sends debris through the cowling or causes an immediate shutdown. The engineers watch these tests carefully. High-speed cameras capture every millisecond of the impact. Sensors measure vibrations, temperatures, pressure changes. After the test, the engine is disassembled and inspected for damage. The goal is to understand not just whether the engine survived, but how it survived, what the failure modes are, where the weaknesses might be, and then they redesign, strengthen, improve, and test again with another frozen chicken. There's something almost absurdly literal about this solution. You need to know if your engine can handle a bird strike. Shoot a bird at it. You don't simulate it with mathematical models or computer simulations. Actually do it physically in the real world, and it works. Modern jet engines are remarkably resilient to bird strikes. Many incidents result in nothing more than a vibration, maybe some damaged fan blades that get replaced during routine maintenance. The catastrophic failures are rare, and they're rare partly because of all those frozen chickens launched at engines during development and testing. It's unglamorous, slightly ridiculous sounding, and absolutely essential. Sometimes the best way to test if something works is to just try to break it and see what happens. When you're sitting in an airplane cabin at cruising altitude, breathing comfortably, reading a book or watching a movie, you might assume the air pressure around you is the same as it would be on the ground, but it's not. The cabin is pressurized, yes, it has to be, because the air outside at 35,000 feet is far too thin to sustain consciousness, but it's not pressurized to sea level. Instead, the cabin pressure is typically equivalent to being at about 8,000 feet of elevation. That's roughly the altitude of a ski resort or a high mountain town or the summit of a modest peak. Why not pressurize the cabin all the way to sea level conditions? It comes down to structural stress. Every time the aircraft climbs to altitude and the cabin pressurizes, there's a pressure differential between inside and outside. The cabin air pushing outward against the fuselage trying to expand, while the thin outside air provides almost no resistance. The greater that pressure difference, the more stress on the aircraft's skin and frame. Pressurizing to 8,000 feet instead of sea level reduces that differential, which means less stress on the structure, which means the aircraft can be lighter and still maintain safety margins. But there's a trade-off, and you're the one experiencing it. At 8,000 feet equivalent altitude, there's less oxygen per breath than at sea level. Not dangerously less, but noticeably less. This is why you might feel slightly lightheaded on a long flight, why you tire more easily, why alcohol affects you more strongly. Your body is functioning at altitude, even though you're sitting still in a comfortable seat. Some people experience headaches or difficulty concentrating. Flight attendants who work these altitudes day after day have to stay hydrated and pace themselves because the reduced oxygen is a constant factor in their working environment. And then there's your ears. As the plane climbs and the cabin pressure drops to that 8,000 foot equivalent, the air inside your ear canals wants to expand. That's the pressure change you feel, the popping sensation as your ears equalize. During descent, the opposite happens. The cabin pressure increases, and now the air in your ears needs to compress to match. For some people, this equalization happens smoothly and automatically. For others, especially with a cold or sinus congestion, it can be uncomfortable or even painful. It's a fascinating compromise when you think about it. We could build aircraft strong enough to maintain sea level pressure at cruising altitude. We have the technology. But it would make the planes heavier, more expensive to build and operate, less fuel efficient. So instead we accept this middle ground. Comfortable enough to keep everyone safe and functional, but not quite the same as being on the ground. You're at 8,000 feet physiologically speaking, even while you're actually at 35,000 feet. Your body is on a mountain while you race across the sky. A strange disconnect between physical reality and the altitude your cells are experiencing. And for most of us, most of the time, that compromise works just fine. Here's a concept that challenges the intuitive understanding of how flight works. Airplane wings don't slice through the air like a knife cutting through butter. They don't defeat the air or ignore it or somehow slip past it with minimal interaction. Instead, they deflect it downward. They push air toward the ground, and it's this downward push, the redirected air, that creates the upward force we call lift. Newton's third law in action. For every action, there's an equal and opposite reaction. Push air down, get pushed up. Most people learn a different explanation in school. Something about air moving faster over the curved top of the wing than the flat bottom, creating a pressure difference that generates lift. That's called Bernoulli's principle, and it's not wrong exactly, but it's incomplete. It describes what's happening with the pressure, but it doesn't really explain why. The more fundamental explanation is momentum exchange. The wing redirects a massive amount of air downward, and the reaction to that redirection is an upward force on the wing. And think of it this way. The wing is meeting air that's moving horizontally, or mostly horizontally from the wing's perspective. As the air flows over and under the wing's curved surfaces, it gets turned, redirected slightly downward. The air leaves the wing travelling at a downward angle compared to how it arrived. And because the plane is moving forward so quickly, the wing is constantly meeting fresh air, constantly deflecting it downward, creating a continuous downward stream of air behind and below the aircraft. This downward moving air is called downwash, and you can actually observe it in certain conditions. If a plane flies low over water, the downwash can create visible ripples on the surface. If it flies over a field of tall grass or crops, you can see the grass flatten in waves as the deflected air rushes over it. It's invisible most of the time, but it's always there. A river of air being pushed toward the earth by the wings passing through it. There's something beautiful about this realization. Flight isn't about defeating gravity or escaping the air. It's about working with the air, redirecting it. using its mass and momentum to generate the force you need. The wing is in constant conversation with the atmosphere, and lift is the result of that conversation. Every second, tons of air are being deflected downward, and in exchange the plane is being pushed upward. It's not magic, though it feels like magic. It's physics. Elegant, continuous, relentless physics. The air doesn't want to be pushed down, so it pushes back, and that pushback keeps hundreds of tons of metal floating through the sky. Push and counter-push. Action and reaction. All the way from takeoff to landing. If you've ever looked closely at a jet engine while it's parked at the gate, maybe you were walking across the tarmac to board, or looking out a window during a delay, you might have noticed something curious painted on the spinner. The cone-shaped nose right in the centre of the engine. There's often a spiral pattern, usually in bright white or yellow, painted in a way that creates a distinctive swirl design. At first glance it seems decorative, maybe branding or aesthetics, but that spiral has a very practical, even critical function. It helps ground crews detect if the engine is spinning. Here's the problem it solves. Jet engines, especially large turbofans, can be dangerously quiet when they're idling or winding down. The massive fan blades at the front can be spinning at hundreds of revolutions per minute without making much noise, especially if you're not directly in front of the engine, or if there's other ambient noise on the ramp, ground equipment running, other planes taxiing, crew members communicating. It's alarmingly easy to approach an engine that looks stationary but is actually still spinning, and that's a deadly mistake. The intake of a jet engine creates powerful suction, and if you get too close you can be pulled in. It's happened tragically more than once. The spiral solves this with elegant simplicity. When the engine is off, the spiral is just a static pattern. But when the engine is running, even at low speed, the spinning motion creates an optical illusion. The spiral appears to be moving, pulsing, animated. Your brain perceives motion even though the painted spiral itself hasn't changed. It's impossible to miss if you're looking at the engine, even from a distance or in your peripheral vision. That animated spiral screams, "Danger, this is spinning," in a way that's intuitive and immediate. It's such a simple solution to a serious problem. No electronics, no sensors, no power source required, just paint, applied in a specific pattern, leveraging how human visual perception works. The spinning engine makes the spiral move, and the moving spiral warns anyone nearby that the engine is running. It's the kind of low-tech brilliance that shows up throughout aviation, using basic physics and psychology to solve problems that could otherwise require complex systems. And there's something oddly mesmerizing about watching those spirals when an engine is running, isn't there? They pulse and swirl, creating motion where there shouldn't be any, a visual trick that serves a life-saving purpose. The next time you're near an aircraft and you see those spirals, maybe appreciate them for what they are. Not decoration, but communication. The engine speaking to anyone nearby in the clearest possible terms. "I'm alive. Stay back." A warning painted in swirls, turning deadly silence into visible motion. Commercial airplanes are designed with a principle called safety margin, and it's more extreme than you might imagine. The structures, the wings, the fuselage, the tail surfaces, the landing gear, are all designed to withstand 1.5 times the maximum stress they should ever experience during normal operation. This is called the limit load factor, but even that's not the ultimate design limit. The aircraft must also be able to withstand what's called the ultimate load, stresses that are 1.5 times greater than that maximum normal load, which works out to 2.25 times normal operational stress. Though for most commercial aircraft, the practical ultimate load factor is around 1.5 times, the limit load of 1.5 G, making it capable of withstanding roughly 2.25 G without catastrophic structural failure. What does this mean in practice? It means that when engineers design an airplane, they calculate the worst forces it's likely to encounter, the most extreme turbulence, the hardest possible landing, the most aggressive maneuver within the flight envelope, and then they design the structure to be strong enough to handle forces well beyond that. Everything from turbulence to hard landings to aggressive turns is well within the aircraft's capability, often not even approaching the design limits. This is why severe turbulence, while frightening, very rarely damages an aircraft structurally. The wings might flex dramatically, you might see them bending up and down by several feet if you're watching from a window seat, and that can be terrifying to witness. But those wings are designed to flex like that. They're designed to handle stresses far greater than what even severe turbulence can produce. The plane is being shaken, certainly, and it's uncomfortable for everyone on board, but the structure itself is nowhere near its limits. Or consider a hard landing, the kind where the plane comes down with a noticeable thump that makes passengers gasp and wonder if something broke. In most cases, that landing was still within the aircraft's design parameters. The landing gear absorbed the impact exactly as designed. Yes, the pilots will report it as a hard landing, and maintenance will inspect the aircraft for any damage, but often there's nothing wrong. The plane was built to handle it. There's something deeply reassuring about this, isn't there? The engineers who designed these aircraft anticipated the worst, and then built in margins well beyond that. They assumed things would go wrong, pilots would make mistakes, weather would be worse than predicted, unexpected forces would occur, and they designed the structure to survive anyway. It's pessimism in service of safety, assuming that Murphy's Law will apply and preparing for it. The result is aircraft that are robust, resilient, able to absorb punishment that would seem catastrophic but is actually well within their capabilities. You're flying in a machine designed to survive much worse than anything you're likely to experience, and somehow that makes the turbulence a little less frightening. Let's talk about power, because the engines on modern wide-body aircraft produce power at scales that are difficult to truly comprehend. A single General Electric GE90 engine, the type used on Boeing 777s, can generate over 110,000 pounds of thrust at full power. To put that in perspective, that's more than the maximum takeoff weight of the entire original Boeing 737. One engine producing more thrust than an entire airplane weighs. But thrust is just one way to measure the engine's power. If you converted that thrust into electrical power, each engine could theoretically generate enough electricity to power a city of 400,000 people. 400,000 people, all their homes, streetlights, businesses, hospitals, everything, powered by one jet engine. Of course, jet engines aren't designed to generate electricity at that scale. They're designed to produce thrust. But the fundamental energy conversion happening inside that engine, the amount of chemical energy being released from burning jet fuel and converted into mechanical work, is enough to supply electricity to a small city. Think about what's happening inside that engine. Air is being pulled in through the massive fan at the front. Tons of air per second compressed to enormous pressures, mixed with fuel, ignited in a continuous combustion process, and then expelled out the back at supersonic speeds. The temperatures inside the combustion chamber exceed 3,000 degrees Fahrenheit, hot enough to melt most metals. The turbine blades that extract energy from that rushing burning gas are spinning at thousands of RPM, while exposed to temperatures that would destroy them if they weren't made from exotic nickel-based alloys and cooled by intricate internal air passages. This isn't just happening. It's happening reliably, continuously, for hours at a time. A trans-Pacific flight might run those engines at high power settings for 12 hours straight. 12 hours of continuous combustion, compression, extreme temperatures and violent rotation, all contained in a structure that weighs only a few tons, but produces power that dwarfs almost anything else humans have built. Modern jet engines are among the most reliable machines ever created, and with failure rates measured in events per million flight hours. There's something almost frightening about this level of power, this controlled violence happening just outside the cabin wall. But there's also something awe-inspiring. We've learned to harness combustion, one of humanity's oldest technologies, and scale it up to these incredible levels while making it incredibly safe and reliable. Each engine is a small power plant, a carefully orchestrated explosion that never stops as long as fuel flows and air enters. And that controlled explosion, repeated in engines on both wings, is what pushes hundreds of people across oceans and continents, what overcomes drag and gravity and carries us to the far side of the world. The power of a small city focused on the singular purpose of flight. There's a reason you feel so dried out on long flights, why your skin feels tight and parched, why your lips crack, why your eyes sting even when you're not tired. The air inside an airplane cabin is extraordinarily dry, typically below 20% relative humidity, and sometimes as low as 10 or 12%. To put that in perspective, the Sahara Desert, one of the driest places on Earth, averages about 25% humidity. You're literally sitting in an environment drier than most deserts, breathing this arid air for hours at a time while your body slowly loses moisture to the atmosphere around you. This isn't an oversight or a cost-cutting measure. It's an inevitable consequence of how cabin air works at altitude. Remember, half the air in the cabin is fresh air pulled from outside the aircraft and compressed. At cruising altitude, the outside air is already incredibly dry. There's almost no moisture in the stratosphere. And when you compress air, even if it contains some water vapor, the compression process heats it, which further reduces the relative humidity. By the time that air is delivered to the cabin, it's been stripped of nearly all its moisture. You might wonder, why not just add moisture back? Humidify the cabin like you'd humidify a house in winter. The problem is weight and corrosion. Water is heavy, 8 pounds per gallon, and you'd need to carry a substantial amount to meaningfully humidify a cabin for a long flight. That extra weight means burning more fuel, which costs money and increases emissions. But even worse is what moisture does to the aircraft structure over time. If you increase cabin humidity, you risk condensation forming inside the walls, the insulation, the structural components, and condensation leads to corrosion, which weakens the airframe. The trade-off isn't worth it, so we accept the dryness, and our bodies cope, though not without complaint. You lose moisture through your skin, through your respiratory system, through every breath you exhale into that thirsty air. Flight attendants, who spend days or weeks every month in these conditions, learn to hydrate aggressively, use moisturizer religiously, carry eye drops. Passengers often don't realize what's happening until they land and notice how awful they feel. headachy, dehydrated, skin feeling like parchment. The advice is simple: drink water, more than you think you need. Your body is losing moisture constantly in that desert air, and you need to replace it. Skip the alcohol and caffeine, both of which dehydrate you further. Use moisturizer if you have it, and maybe, just maybe, appreciate the strange environment you're in. Drier than a desert, 6 miles above the earth, breathing air that's been compressed and filtered and heated, all so you can cross continents in hours instead of weeks. The dryness is uncomfortable, certainly, but it's a small price for the miracle of pressurized flight. Your lips might crack, but you're breathing comfortably in an environment that would kill you in minutes without that carefully controlled, desert dry air flowing through the cabin. There's a flight that operates between Singapore and New York, specifically between Singapore Changi Airport and John F. Kennedy International Airport. That holds the record for the longest non-stop commercial flight in the world. It covers 9,537 miles, roughly the distance you'd travel if you drove from New York to Los Angeles more than 3 times. The scheduled duration is about 18 hours, though it can vary depending on winds. 18 hours. That's a significant portion of a full day, spent entirely in the air, crossing half the globe without touching down. Think about what that means for the passengers. You board in Singapore as the sun is setting. You're served dinner, maybe you watch a movie or two, try to sleep in your seat. You wake up, still flying, breakfast is served, you read, work, watch more movies, lunch comes, you're still flying. The sun rises and sets outside your window, or doesn't, depending on which direction you're travelling and what the sky looks like from your seat. You cross 15 time zones, your body's circadian rhythms completely scrambled by the experience of compressing what should be multiple days of travel into a single continuous journey. For the crew, it's a unique challenge. Flight attendants work in shifts, but they're all on the same airplane for those 18 hours, managing passengers who are increasingly restless, tired, uncomfortable. Pilots rotate in and out of the cockpit, resting in crew bunks, but still subject to the same time zone confusion, the same disruption of normal sleep patterns. The plane itself is pushed to its limits, not dangerously, but operationally. Fuel efficiency matters enormously on a flight this long. Every kilogram of weight, every headwind, every deviation from the optimal flight path has compounding effects over such distance. And yet, people choose this flight. They pay for tickets, board willingly, spend 18 hours in a metal tube because it's the fastest way to get from Singapore to New York. The alternative would be stopping somewhere, Dubai perhaps or Europe, adding layover time that could stretch the total journey to 24 hours or more. So they choose the marathon flight, the endurance test, trading comfort for efficiency. There's something both impressive and slightly absurd about this, isn't there? We've built aircraft capable of flying for nearly a full day without stopping. We've solved the engineering challenges, fuel capacity, engine reliability, crew rest requirements, passenger needs. But we haven't solved the fundamental problem of the human body not being designed for this. You arrive in New York having crossed 15 time zones, and your body has no idea what time it is, what day it is, whether you should be sleeping or eating or functioning normally. The airplane delivered you efficiently, reliably, safely across half the Earth. But your circadian rhythms will need days to catch up to where you actually are. Distance collapsed, time confused, geography conquered. That's the reality of the longest non-stop flight in the world. Look at an airplane from the front, or better yet, look at a photograph taken head-on. where you can see the wings extending on both sides. And you'll notice something subtle. The wings aren't perfectly horizontal. Yeah, they angle slightly upward from where they attach to the fuselage out to the tips. This upward angle is called dihedral, and it's one of those design features that's invisible to most passengers, but absolutely essential to how the plane flies. The purpose of dihedral is stability, specifically stability in the roll axis. That's the side-to-side tilting motion. Imagine the plane gets disturbed by a gust of wind, causing one wing to dip lower than the other. Without dihedral, the plane would just stay tilted until the pilot corrected it. But with dihedral, something clever happens automatically. When one wing drops, that lower wing is now presented to the oncoming air at a slightly different angle than the higher wing. The lower wing generates more lift because it's meeting the relative wind more directly. That increased lift pushes the wing back up, naturally correcting the tilt without any pilot input. It's passive stability, built into the shape itself, requiring no active control systems, no computers, no pilot intervention. The airplane wants to return to level flight because of its geometry. It's the same principle that makes a pendulum swing back to center, or why a ball rolls to the bottom of a bowl. The shape creates forces that resist disturbance and promote equilibrium. Different aircraft have different amounts of dihedral depending on their purpose and design. Small, stable aircraft designed for training or cruising might have pronounced dihedral because stability is paramount. Fighter jets, on the other hand, often have very little dihedral or even the opposite, anhedral, where the wings angle downward because they prioritize maneuverability over stability. They want to be able to roll quickly, to respond instantly to pilot input, even if that means sacrificing natural stability. There's something elegant about dihedral that's worth pausing on. It's a solution that requires no power, no maintenance, no active input. It's just geometry, just the wings angled slightly upward, creating forces that keep the plane level. When you see an aircraft in flight, maybe notice those wings, how they rise gently from the fuselage to the tips. That subtle angle is doing invisible work every moment, every gust of wind, keeping the plane stable without anyone noticing or thinking about it. It's one more example of how good design often means building in behaviors that work automatically, quietly, more reliably, solving problems before they become problems, maintaining balance without drama or intervention. The ASIR-71 Blackbird is a plane that seems to exist at the edge of what's physically possible. It was a spy plane, designed in the 1960s to fly reconnaissance missions over hostile territory at speeds and altitudes where nothing could catch it or shoot it down. It flew at Mach 3.2, over 3 times the speed of sound, roughly 2,200 miles per hour, at altitudes above 85,000 feet, high enough that pilots could see the curvature of the Earth and the darkness of space above them. At those speeds, something extraordinary happened to the aircraft itself. Friction with the air generated so much heat that the titanium skin would reach temperatures over 600 degrees Fahrenheit. 600 degrees! Hot enough to boil water instantly. Hot enough to burn skin on contact. Hot enough to make the metal glow faintly if you were in a dark room. And this heat didn't just warm the aircraft, it actually caused the entire airframe to expand. The SR-71 would grow by several inches during flight as the metal heated and expanded, panels shifting, gaps opening and closing. In fact, the fuel tanks weren't even properly sealed when the plane was on the ground. They leaked. Fuel would drip from the tanks while the plane sat on the tarmac. and ground crews just accepted this as normal. The seals and panels were designed for the expanded, heated shape of the aircraft in flight, not the cold, contracted shape on the ground. So the SR-71 would take off with fuel dripping from it, climb to altitude, accelerate to Mach 3, heat up, expand, and only then would the tanks seal properly as the gaps closed and the panels fitted together correctly. This meant the plane had to be refueled shortly after takeoff. It couldn't carry enough fuel to complete a mission starting from the ground. It burned through fuel too quickly during the acceleration to cruise speed. So the procedure was to take off, climb, accelerate, rendezvous with a tanker aircraft, refuel in mid-air now that the tanks were properly sealed, and then continue with the mission. It was operationally complex, but it was necessary given the physics involved. Think about what this represents. We built a plane that flew so fast it had to be designed for two different states, cold and leaky on the ground, hot and sealed in flight. A plane where the fuel tanks leaking was not a malfunction, but an expected characteristic. A plane that experienced thermal expansion so extreme that dimensions changed by inches, and it worked. The SR-71 flew hundreds of missions and was never shot down, never caught, never even seriously threatened. It simply outran everything: missiles, interceptors, surface-to-air defences. Speed and altitude were its protection, and the heat was the price paid for that speed. The Blackbird doesn't fly anymore. It was retired decades ago, but it remains a testament to how far we can push engineering when we're willing to accept extreme solutions to extreme challenges. Airplanes don't last forever. Even with meticulous maintenance, even with every component checked and rechecked, even with parts replaced on strict schedules, eventually the aircraft reaches the end of its service life. But it's not because the engines stop working or the systems fail. It's because of something more subtle and insidious: metal fatigue. Every time an airplane takes off and lands, the fuselage goes through what's called a pressurization cycle. On the ground, the interior and exterior pressure are the same. As the plane climbs, the cabin is pressurized while the outside pressure drops. The fuselage expands slightly like a balloon being inflated. During descent and landing, the cabin depressurizes and the fuselage contracts. This expansion and contraction happens with every flight, every single time the plane goes up and comes back down, and metal, for all its strength, isn't infinitely flexible. Every time it bends, every time it flexes, microscopic changes occur in the material structure. Crystals shift, tiny cracks form, nothing visible, nothing you could detect without specialized equipment. But the damage accumulates. Over thousands of cycles, those microscopic cracks grow. The metal becomes work-hardened in some places, brittle in others. Stress concentrates at rivet holes, around window frames. Anywhere there's a discontinuity in the structure. This is why aircraft have service lives measured not just in years, but in pressurization cycles. A plane that makes short flights, taking off and landing multiple times per day, accumulates cycles faster than a plane making long international flights. The calendar age might be the same, but the structural fatigue is different. Inspectors look for signs of this fatigue, using everything from visual inspections to ultrasound and X-ray imaging to detect cracks before they become dangerous. Eventually, the cumulative fatigue reaches a point where the cost of inspection and repair exceeds the value of keeping the plane flying, or the risk becomes unacceptable. There are only so many times you can repair and reinforce before the structure becomes fundamentally compromised. So the plane is retired. Not because it suddenly broke, not because it stopped working, but because it's been bent and flexed and stressed so many times that it simply can't be trusted anymore. There's something almost melancholic about this. These machines that carried millions of people safely across billions of miles, that survived storms and crosswinds and hard landings, that functioned reliably for decades, they're eventually worn out not by catastrophic failure but by the accumulated weight of all those successful flights. Every takeoff, every landing, every pressurization cycle adding to the invisible fatigue until finally the metal says no more. They're retired to desert boneyards where the dry air preserves them, or they're disassembled for parts, or they're scrapped entirely. The metal that flexed so many thousands of times finally gets to rest, its service complete, worn out by the very thing it was designed to do. When you watch an airplane prepare for takeoff or landing, you might notice the wings seem to transform. Panels extend from the front and back edges, changing the wing's shape dramatically. These are flaps and slats, movable surfaces that deploy during low-speed flight, and they can increase the wing surface area by up to 50%. 50%. The wing becomes, quite literally, a completely different shape. It's just optimized for a completely different purpose than the sleek, streamlined wing designed for high-speed cruise. Here's why this matters. A wing that's perfect for cruising at 500 miles per hour at 35,000 feet is terrible for flying slowly near the ground. At cruise, you want minimum drag, a thin profile, efficiency. But during takeoff and landing, you're moving much slower, maybe 150 to 180 miles per hour. And at those speeds, the clean wing doesn't generate enough lift. You'd either need to fly dangerously fast to maintain enough lift, or you'd fall out of the sky. So the wing changes shape. Slats extend from the leading edge, the front of the wing increasing camber and allowing the wing to operate at higher angles of attack without stalling. Flaps extend from the trailing edge, the back of the wing, in increasing both surface area and curvature. Together they transform the wing into a shape that generates tremendous lift even at low speeds. The downside is drag, lots of it. The deployed flaps and slats create so much drag that you'd never cruise this way. The fuel consumption would be astronomical, but for the brief periods during takeoff and landing, that drag is acceptable. You need the lift more than you need efficiency. Watch the sequence during landing, and you'll see it happen in stages. The pilot extends the flaps gradually. First just a little, then more, then full extension as the plane slows for final approach. Each stage is a compromise between the lift you need and the drag you can tolerate at your current speed. Too much flap too early, and the drag becomes overwhelming. Too little flap too late, and you don't have enough lift to maintain a safe descent rate. The timing and sequence are carefully planned, practiced until they become automatic, and then, after landing, the flaps retract. The slats fold back into the wing. The surface area shrinks, the shape streamlines, and the wing returns to its cruise configuration. It's a transformation that happens dozens of times per day on commercial aircraft, so routine that we barely notice it. But think about what it represents. A wing that can be two different things, optimized for two completely different flight regimes, changing shape on demand to match the immediate requirements. It's adaptive design at a fundamental level, the airframe itself reconfiguring to meet changing needs. Not many things we build have this capability. Most are optimized for one purpose and one purpose only. But wings have to serve multiple masters, speed and efficiency during cruise, lift and control during takeoff and landing. So they change, they adapt, they become what they need to be in the moment, and it's beautiful to watch if you know what you're seeing. Here's an urban legend that refuses to die, one that seems to circulate constantly in popular culture. The idea that airplanes dump their toilet waste mid-flight, raining sewage down on unsuspecting people below. The image is vivid, slightly horrifying and completely false. Airplane waste is not dumped mid-flight. It's stored in sealed tanks and removed during ground servicing, just like waste from any other vehicle or building. Yeah, the confusion might come from something real but rare. Blue ice. Very occasionally, and this is genuinely uncommon, a toilet valve on an aircraft can develop a leak. When this happens, a small amount of waste mixed with the blue disinfectant used in airplane toilets can leak from the valve assembly on the exterior of the aircraft. At cruising altitude, where temperatures are 70 degrees below zero, this leaked fluid immediately freezes into a chunk of ice. That ice might stay attached to the aircraft, or it might break off during descent when the air warms. If it falls, it's falling as a frozen chunk that can survive long enough to reach the ground, hence the nickname blue ice. But these incidents are rare, documented and investigated when they occur. They're maintenance issues, not standard procedure. The vast majority of flights operate with perfectly sealed systems where nothing escapes the aircraft. Every drop of waste generated during the flight stays in the holding tanks until ground crews service them after landing. It's unglamorous work. There are trucks designed specifically for this purpose, connecting to the aircraft's waste service panel and pumping the contents out. But it's how the system actually works. The persistence of the dumping myth says something interesting about how we think about technology and infrastructure. We're comfortable with abstractions. Waste goes away somehow, but we don't always think through the logistics. Where would it go? How would it work? The reality is more mundane than the myth. Sealed tanks, ground servicing, proper disposal. Yeah, not dramatically different from an RV or a marine toilet or any other self-contained waste system. But maybe there's also something reassuring about understanding this. You're not going to be hit by falling airplane waste. That's not a thing that happens, despite what you might have heard. The actual system is designed, regulated, maintained, and monitored to ensure waste stays contained until it can be properly disposed of. It's one more example of how commercial aviation handles thousands of small practical challenges, some of them unpleasant to think about, all of them solved through careful engineering and strict procedures. The toilets work, the waste is contained, and nobody below is at risk from a blue ice incident, except in the rarest of circumstances when a valve fails and an investigation follows. Most of the time, everything works exactly as designed, invisible and unremarkable, which is exactly how it should be. The Boeing 787. Dreamliner represents a significant departure from traditional aircraft design, and you can't see the most important difference just by looking at it. The fuselage, the main body of the aircraft, is made primarily from carbon fiber composite rather than aluminum. This might not sound revolutionary, but it changes almost everything about how the plane performs and how passengers experience the flight. Carbon fiber composite is lighter than aluminum for the same strength. This weight savings translates directly into better fuel efficiency, longer range, or the ability to carry more passengers and cargo. But the real advantage isn't just weight, it's how carbon fiber behaves under stress. Aluminum fatigues over time. developing microscopic cracks that grow with repeated pressurization cycles. Carbon fiber doesn't fatigue the same way. It's more resistant to corrosion, doesn't need the same protective coatings, and maintains its structural properties better over the aircraft's service life. And here's where it gets interesting for passengers, because carbon fiber is stronger for its weight and more resistant to corrosion. Boeing was able to increase the cabin pressure and humidity levels. Remember earlier when we talked about cabin pressure being equivalent to 8,000 feet? The 787 maintains cabin pressure equivalent to 6,000 feet, noticeably lower, which means more oxygen per breath, less stress on your body during long flights, and the humidity can be higher, not dramatically higher. Yes, but enough that the air doesn't feel quite so desiccating, quite so harsh on your skin and respiratory system. You might not consciously notice these differences during a flight, but studies suggest passengers arrive feeling less fatigued, less dehydrated, less jet-lagged after flying on a 787 compared to similar flights on aluminum aircraft. It's subtle, but it's real. The composite structure allows for an environment that's slightly more comfortable, slightly less physiologically stressful. Your body doesn't have to work quite as hard to compensate for the altitude and dryness. Of course, there are trade-offs. Carbon fiber is more expensive to manufacture than aluminum. Repairs are more complex. You can't just rivet a patch over a damaged area like you can with aluminum skin. The manufacturing process requires specialized facilities, autoclaves large enough to cure entire fuselage sections, expertise that traditional aluminum aircraft didn't require. But Boeing decided the advantages outweighed the challenges, and the 787 has become one of the most popular wide-body aircraft in service. There's something quietly revolutionary about this shift to composites. For decades, aircraft were built from aluminum because that was the best material available. Strong enough, light enough, workable enough, but composite materials offered something better, and the industry adapted. The plane looks similar to other aircraft from the outside, but the fundamental material has changed, and with it, the passenger experience has improved in small but meaningful ways. You're flying in a carbon fiber tube instead of an aluminum one, breathing slightly more oxygen. You're feeling slightly less dried out, arriving slightly less exhausted. Progress doesn't always announce itself loudly. Sometimes it's just a different material, quietly making things a little bit better. Here's a fact that exists at the intersection of physics and philosophy. Too small to matter practically, but too fascinating not to think about. Airplane pilots experience time dilation. It's a real effect predicted by Einstein's special relativity. The faster you move through space, the slower you move through time relative to someone who's stationary. And pilots, spending their careers travelling at high speeds relative to the ground, age very slightly slower than people who stay earthbound. The effect is infinitesimally small. We're not talking about pilots returning from a flight to find years have passed on the ground like some science fiction story. The actual difference is measured in nanoseconds, maybe microseconds over an entire career. If you flew commercially for 40 years, you might age perhaps a few hundred microseconds less than someone who never flew. That's millionths of a second. Utterly insignificant in practical terms, unmeasurable without atomic clocks, completely imperceptible to anyone involved. But it's real. The mathematics of special relativity are clear. Moving at 500 miles per hour for tens of thousands of hours adds up to measurable time dilation. Experiments with atomic clocks on aircraft have confirmed this. When you take a precise clock on a flight and compare it to an identical clock that stayed on the ground, The flying clock runs slightly slower. The difference is tiny, but it's there, exactly as Einstein predicted, and there's something delightful about this, isn't there? The fact that pilots are literally travelling into the future, just barely, just by an amount so small it might as well be zero, but nevertheless doing it. Every flight moves them fractionally further ahead in time relative to the rest of us. They're time travellers, technically speaking, even if the travel is measured in millionths of seconds and has no practical consequence whatsoever. It connects everyday experience, getting on a plane, flying across the country, to one of the most profound insights in physics. That time is not absolute, that it flows at different rates depending on your motion through space. Most of us know about time dilation as an abstract concept, weighs something that matters for GPS satellites or particle accelerators or astronauts on the space station, but it's happening on every commercial flight too, just barely. Just enough to measure with precise instruments, just enough to remind us that the universe is stranger than our everyday experience suggests, that even mundane activities like flying from one city to another involve physics that would have seemed impossible a century ago. Pilots age a few microseconds slower. And somewhere in that tiny, practically meaningless fact is a connection to the deepest truths about how space and time actually work. The white trails left by airplanes, those contrails we talked about earlier, aren't just visible markers of air traffic. They actually affect weather and climate in ways that scientists are still working to fully understand. When conditions are right, contrails can persist for hours, spreading out and eventually forming thin cirrus clouds that cover vast areas of the sky. And these clouds, whether they started as natural cirrus or began as contrails, have a measurable impact on how heat moves through the atmosphere. Here's how it works. During the day, these high-altitude clouds reflect some sunlight back into space, which has a cooling effect. But they also trap heat radiating from the Earth's surface, especially at night, which has a warming effect. The net result depends on many factors: the time of day, the thickness and coverage of the clouds, the reflectivity of the ground below, but studies suggest the warming effect generally dominates. Contrail-induced clouds trap more heat than they reflect, contributing to overall warming of the atmosphere, and the magnitude of this effect is still being quantified. But some research suggests that the radiative forcing from contrails, the change in Earth's energy balance they create, might be comparable to or even exceed the warming effect from aviation's CO2 emissions. That's a startling possibility. We focus so much on carbon emissions, on fuel consumption and greenhouse gases, that we sometimes overlook these secondary effects. But the clouds themselves, these artificial cirrus layers created by aircraft exhaust, might be changing the climate in ways that are significant and difficult to model, and it's not uniform. Contrails don't form on every flight. Remember, they require cold, humid air at altitude. So some routes, some altitudes, some weather conditions produce far more persistent contrails than others. There's active research into contrail avoidance strategies, flying at slightly different altitudes or routing around areas where contrails would persist, accepting a small fuel penalty to avoid creating these warming clouds. It's a trade-off. Burn slightly more fuel to avoid creating clouds that trap even more heat. This is one of those environmental challenges that's complex and subtle. Aviation contributes to climate change not just through the direct emissions from burning jet fuel, but through these indirect effects on cloud cover and radiative balance. The full picture is still emerging, but it's clear that those white lines across the sky aren't just visual pollution, They're active participants in the climate system, changing how energy flows through the atmosphere in ways we're only beginning to understand and measure. Down every contrail is a temporary cloud, and every cloud changes how the planet absorbs and radiates heat. At scale, across thousands of flights per day, that adds up to something significant. The trails we leave aren't just markers of where we've been, they're modifications to the sky itself, subtle but real, beautiful from below but consequential for the atmosphere above. There's an invisible barrier in the sky that commercial aircraft approach but never quite cross: the speed of sound. You might think an airplane's maximum speed is limited by how much power the engines can produce, how much thrust they can generate. But for most commercial jets, that's not the limiting factor at all. The real limit is compressibility. What happens to air when you approach the speed at which sound waves propagate through it? At sea level, any sound travels at about 767 miles per hour. At cruising altitude, where the air is much colder, sound travels slower, around 660 miles per hour. As an aircraft accelerates toward this speed, something strange starts happening to the airflow around it. Air that's moving smoothly over the wings and fuselage begins to compress, bunching up into shock waves, regions where the air pressure, density and temperature change dramatically over very short distances. These shock waves create enormous drag, far more than the aircraft experiences at subsonic speeds. They also cause control problems, making the plane harder to maneuver, potentially creating dangerous vibrations. This phenomenon is why commercial jets cruise at speeds around Mach 0.85. That's 85% of the speed of sound. They're deliberately staying well below that invisible barrier where the physics changes, where compressibility effects become severe. Push much faster, and you'd need fundamentally different designs, swept-back wings, different engine configurations, structural reinforcements to handle the buffeting and stress. You'd be building a supersonic aircraft like the Concorde was, and that requires compromises in efficiency, capacity and cost that modern airlines aren't willing to make. So there's this strange situation where the engines could potentially push the plane faster, but doing so would be counterproductive. The drag would increase so dramatically that fuel consumption would skyrocket. The ride would become rough. Systems could be damaged. Instead, the aircraft cruises just below the speed of sound, i.e. in that sweet spot where subsonic physics still applies, where airflow remains predictable and manageable, where efficiency is maximized. It's a wall made of compressed air, of shock waves and turbulence, of the fundamental physics of how pressure propagates through a fluid medium. And commercial aviation has collectively decided not to break through that wall, at least not since the Concorde retired. We could go faster, we've proven that, but the costs exceed the benefits for passenger travel. So we cruise at Mach 0.85 just below the barrier, fast enough to cross oceans in hours but slow enough to avoid the complications of supersonic flight. The sound barrier is still there, still a real limit, still shaping how we fly, even though we have the technology to break through it. Sometimes the best solution is to work within the limits rather than pushing past them, to find the optimal point just below where the physics turns hostile. Step into almost any commercial aircraft cockpit anywhere in the world, and you'll notice something remarkable. The layout looks familiar. Not identical, certainly. Different aircraft models have different specific arrangements, but fundamentally similar. The primary flight instruments are in the same general locations. The throttle controls are positioned consistently. The basic logic of how information is presented follows standard patterns. This isn't an accident. It's the result of decades of standardization, an intentional effort to make cockpits predictable and learnable across different aircraft types. The reason is both practical and safety-oriented. Then pilots often transition between different aircraft during their careers. A pilot might start on regional jets, move to narrow-body aircraft like the 737 or A320, eventually transition to wide-body long-haul planes. Each aircraft has unique characteristics, different systems, different handling qualities. But if the basic cockpit layout were completely different for each type, the learning curve would be enormous, and the risk of errors would increase dramatically. Standardization means a pilot moving to a new aircraft type can leverage their existing knowledge, their muscle memory, their mental models of how things should work. This standardization extends beyond just physical layout. There are international standards for how information is displayed, what colors mean, how warnings are prioritized. A red warning light means the same thing on a Boeing as on an Airbus. Critical instruments are always within the pilot's primary field of view. Backup systems are positioned logically relative to primary systems. The standards are so thorough that a pilot from any country, trained on any aircraft, can step into an unfamiliar cockpit and understand the basic layout within moments. Of course, this doesn't mean any pilot can fly any plane without training. Type ratings exist for good reason. Each aircraft requires specific knowledge about its systems, performance characteristics, limitations. But the standardization means that training focuses on the unique aspects of that particular aircraft, not on relearning fundamental cockpit organization from scratch. It's efficiency through consistency, safety through predictability. And there's something oddly comforting about this, isn't there? In a world where different manufacturers compete, where national pride and corporate interest could drive toward completely different approaches, there's instead this consensus that some things should be standard. A Boeing pilot can look at an Airbus cockpit and immediately orient themselves. A pilot trained in Europe can fly American aircraft without being completely lost. The language of aviation transcends brands and borders, built on shared standards that prioritize safety and interoperability over individual innovation. The cockpit is standardized not because creativity is discouraged, but because lives depend on pilots being able to find what they need when they need it. Without confusion or delay, consistency saves lives. And so the instruments are where you expect them to be, doing what you expect them to do, in every cockpit around the world. During most of a flight, airplane rudders, those vertical control surfaces on the tail that move left and right, are barely used at all. This surprises many people. You'd think steering an airplane would involve the rudder, just like steering a boat involves a rudder. But aircraft don't really steer in the conventional sense, especially during cruise flight. Instead, most turns are coordinated using the ailerons on the wings and slight banking. Here's how it works. To turn left, the pilot rolls the aircraft left by deflecting the ailerons. The left aileron goes up, reducing lift on that wing, while the right aileron goes down, increasing lift on that wing. This tilts the aircraft, banking it into the turn. Although once banked, the lift force, which is no longer pointing straight up, has a horizontal component that pulls the aircraft around the turn. It's elegant, efficient, and requires minimal rudder input. The plane turns by tilting and letting the lift vector do the work. So when do pilots use the rudder? Primarily during crosswind landings, one of the more challenging maneuvers in aviation. Imagine landing with a strong wind blowing from the side. If the pilot simply points the nose at the runway and flies straight in, the wind will push the aircraft sideways, off the center line. Instead, the pilot has to point the nose slightly into the wind, a technique called crabbing, to maintain alignment with the runway. But you can't land with the nose pointed sideways. The landing gear isn't designed for that. So at the last moment, just before touchdown, the pilot uses the rudder to swing the nose around to align with the runway while using the ailerons to keep the wings level. It's a coordinated dance of control inputs, and the rudder is essential. The rudder is also critical during engine failures, especially on takeoff. If one engine fails while the other is at full power, the asymmetric thrust tries to yaw the aircraft, spin it around the failed engine. The pilot uses heavy rudder input to counteract this, keeping the nose pointed straight while climbing on the remaining engine. Without rudder authority, maintaining control would be nearly impossible, so the rudder isn't useless, far from it. But its role is specialized, coming into play during specific situations rather than being constantly active during normal flight. Most of the time it's just along for the ride, making small corrections to keep the aircraft coordinated but not doing the heavy lifting of turning the plane. It's another example of how flying works differently than our intuition suggests. We think of rudders as steering devices because that's how they work on boats. But in the air, with 3 dimensions to move through and lift forces to work with, the logic is different. The rudder is there when you need it, critical in certain moments, but quietly idle during most of the flight. One more control surface doing its specific job in the larger symphony of forces that keep the aircraft flying where it needs to go. The U-2 spy plane flies at altitudes so extreme that the pilots might as well be astronauts. At operational ceiling, over 70,000 feet, the air is so thin that it barely qualifies as atmosphere anymore. The pressure is less than 2% of sea level pressure. If the cockpit lost pressurization at that altitude, the pilot would have about 15 seconds of useful consciousness before hypoxia rendered them incapacitated. Water boils at room temperature in that environment. Without a pressure suit, your blood would literally boil, so U-2 pilots wear full pressure suits, very similar to what astronauts wear. These aren't just oxygen masks and flight suits, they're sealed garments that maintain pressure around the pilot's body, with helmets that lock on, gloves that seal, life support systems that regulate temperature and oxygen. The process of putting one on takes over an hour and requires assistance. Once suited and seated in the aircraft, the pilot is essentially in a personal spacecraft. We isolated from the hostile environment outside by layers of fabric and technology. And the view from up there, it's otherworldly. At 70,000 feet, you're higher than most weather, higher than commercial traffic, higher than nearly everything that flies. The sky above appears dark purple or even black, because there's so little atmosphere left to scatter sunlight. During the day you can see the curvature of the Earth clearly, the planet's edge curving away beneath you. Stars become visible even in daylight. You're at the edge of space, not quite in orbit, but close enough to see what astronauts see. The thinness of the atmosphere, the fragility of that blue layer between Earth's surface and the void. Flying at this altitude is technically challenging in ways that most aviation never encounters. The air is so thin that the margin between maximum speed and stall speed becomes razor thin, something called coffin corner. Fly too slow and you stall because there's not enough air over the wings to generate lift. Fly too fast and you approach the speed of sound, where shock waves create control problems. The acceptable speed range might be only a few knots, requiring constant attention and precise control. The U-2 was designed during the Cold War for reconnaissance missions over the Soviet Union and other denied territories, flying so high that interceptor aircraft and surface-to-air missiles couldn't reach it. Even today, despite advances in satellite technology and drones, the U-2 remains in service because it offers capabilities that nothing else quite matches. Extended loiter time, sophisticated sensors, even the ability to react and redirect during missions. It's a relic of a different era of aviation, a plane designed to fly at the edge of what's possible, requiring pilots to dress like astronauts and accept risks that seem excessive in the modern age of automated systems and unmanned platforms. But it still flies, still climbs to those extreme altitudes where the sky turns dark and the Earth curves visibly below, still carries humans into an environment that's barely distinguishable from space itself. Aircraft wings are incredibly strong, engineered to handle forces far beyond what they'll normally experience. But no structure is infinitely strong, and engineers have to consider what happens if a wing is subjected to stresses beyond its design limits. So, here's something fascinating about how aircraft are designed. If a wing is going to fail, and to be clear, this is extraordinarily unlikely, it's intentionally designed to fail upward rather than downward. What does that mean? Imagine forces so extreme that the wing structure begins to give way. The design ensures that the wing bends upward, folding up over the fuselage rather than breaking off and falling away. The failure mode is controlled, directed, engineered into the structure itself. This happens through careful choices about where to place structural members, which materials to use, how to orient fibers in composite materials, where to design in controlled failure points. The reason is obvious once you think about it. A wing that folds upward, even catastrophically, keeps the major structural elements attached to the aircraft. It might disable flight, but it doesn't immediately send the plane tumbling out of control. A wing that breaks off completely, on the other hand, creates an instant, unrecoverable emergency. The aircraft loses lift on one side, the center of gravity shifts dramatically. Control becomes impossible. By engineering the failure mode to bend upward instead of breaking away, designers are planning for the absolute worst-case scenario in a way that maximizes whatever slim chance of survival might exist. Again, it's worth emphasizing, this is theoretical. Modern aircraft wings don't fail during normal operation, or even during most abnormal situations. They're tested to destruction during certification, subjected to bending forces far beyond anything they'll experience in service, and they handle it. The videos of wing stress tests are remarkable. Wings bent upward until the tips nearly touch, flexing by 20 or 30 feet, holding that position for sustained periods, and then returning to normal shape without permanent damage. The point at which actual structural failure occurs is well beyond anything that happens in real-world flight. But the fact that engineers think about controlled failure modes, that they design the structure to fail in a specific, less catastrophic way if the unthinkable happens, is a testament to how deeply safety thinking is embedded in aircraft design. It's not enough to make the wings strong enough for any conceivable situation. You also have to think about what happens if somehow, impossibly, that isn't enough, and you design the failure to be as survivable as possible. It's pessimistic thinking in service of safety, assuming the worst and planning for it, ensuring that even in scenarios that should never happen, the aircraft behaves in ways that maximize whatever small chance of survival exists. The wings are designed to bend upward if they're going to fail. Hopefully, they never will. But if they do, even that has been thought through, engineered, controlled. Tucked away in the tail section of most commercial airliners is a small but crucial piece of equipment called the APU, the Auxiliary Power Unit. It's essentially a miniature jet engine, much smaller than the main engines that provide thrust for flight, but vital for getting those larger engines started and keeping systems running when the aircraft is on the ground without external power. Think about the problem it solves. When a commercial jet is parked at the gate, the main engines are shut down, but the aircraft still needs power, electrical systems for lighting, air conditioning to keep the cabin comfortable, hydraulics for cargo loading, computers for flight planning. Without the APU, the plane would need to be connected to ground power units, essentially giant power cords plugged into the airport's electrical system. And when it's time to start the main engines, you'd need external air carts to provide the high-pressure air that spins the engine turbines fast enough to begin the combustion process. The APU makes all of this self-contained. It's a small turbine engine that burns fuel to generate both electricity and compressed air. It can power all the aircraft systems while parked, providing air conditioning so passengers can board comfortably. And critically, it provides the compressed air needed to start the main engines. The APU is essentially the airplane's starter motor, scaled up to produce enough power to spin massive jet engines to starting speed. When you're sitting in an airplane at the gate, doors close but not yet moving, and you hear a subtle change in the background noise, a slight whine, a shift in the air conditioning flow. That's often the APU starting up. It's small enough that it doesn't shake the aircraft or create the distinctive roar of the main engines, but it's powerful enough to generate more electricity than several houses would use. Enough compressed air to start engines weighing several tons. And here's what's interesting. The APU is itself a jet engine, and running on the same basic principles as the engines that will eventually push the plane through the sky. Combustion, turbine blades, compression, energy extraction, all of it happening in a package much smaller than the main engines, but still incredibly sophisticated. It's a complete power plant, self-contained, capable of running for hours if needed, providing independence from ground infrastructure. There's an elegant recursion to this, isn't there? A small engine that exists solely to start bigger engines, to provide power when the main power sources can't run. It's redundancy and self-sufficiency built into the aircraft, ensuring that the plane doesn't depend entirely on external support to function. The APU is rarely noticed by passengers, never discussed unless it malfunctions, but it's working hard during every turnaround, by every boarding process, every engine start sequence. A little engine with a big job, the airplane's starter motor and portable power station, quietly making sure the aircraft can function independently, whether connected to ground power or sitting alone on a remote parking stand far from the terminal. Modern flight simulators have become so realistic, so convincing in their recreation of flight, that pilots can log hundreds of hours without ever leaving the ground. These aren't simple video game setups. They're full-motion simulators costing tens of millions of dollars, exact replicas of actual cockpits mounted on hydraulic platforms that can pitch, roll and yaw to recreate the sensations of flight. The visual systems project realistic scenery from every window, updating in real time as the simulated aircraft moves. The sounds are perfect. Engine noise, wind, system warnings, everything calibrated to match reality. And the fidelity is so high that pilots report feeling genuinely airsick during training. The motion systems can replicate turbulence so convincingly the visual systems can create such realistic motion cues that the pilot's inner ear and visual systems send signals to the brain indistinguishable from actual flight. Your body doesn't know you're sitting in a room at ground level. As far as your vestibular system is concerned, you're banking, pitching, experiencing G-forces, moving through space. Some pilots need motion sickness medication for simulator sessions, which seems almost absurd, getting sick from simulated flight. But it's a testament to how realistic these systems have become. This realism serves a critical purpose. There are scenarios that are simply too dangerous to practice in actual aircraft. Engine failures on takeoff, hydraulic system malfunctions, electrical fires, severe wind shear during landing, cockpit depressurization, the simultaneous failure of multiple systems. In a real aircraft, these scenarios could be catastrophic. Even attempting to practice them introduces unacceptable risk. But in a simulator, pilots can practice these emergencies repeatedly, developing the muscle memory and decision-making skills needed to handle them without any actual danger. Airlines now do most of their pilot training in simulators. Initial qualification, recurrent training, checks and evaluations, all conducted in these sophisticated devices. A pilot can fly hundreds of approaches to challenging airports they've never actually visited, practice crosswind landings in conditions worse than they'd ever deliberately encounter, experience the handling characteristics of their aircraft with various system failures, all without burning fuel or risking equipment or lives. The time in actual aircraft is reserved for normal operations and for validating that simulator-acquired skills transfer to reality. And they do transfer remarkably well. The muscle memory developed in the simulator translates directly to the real cockpit. The decision-making processes practiced during simulated emergencies apply when actual problems occur. There have been cases where pilots successfully handled serious emergencies, and when interviewed afterward, they credited their simulator training. They'd practiced exactly this scenario, knew exactly what to do, the executed procedures they'd rehearsed dozens of times in a device that never left the ground. It's a strange evolution in aviation. Flying used to be something you could only learn by doing, by actually leaving the ground and accumulating experience in the air. But now much of that learning happens in sophisticated replicas that convince your brain and body they're experiencing flight while you remain safely on the ground. These simulators don't replace actual flight experience, but they augment it tremendously, allowing pilots to safely explore the edges of the flight envelope, to practice scenarios they hope never to encounter in reality, to fail and learn and improve without consequences. And when they do step into a real cockpit, they're better prepared, more experienced with emergencies, more confident in their ability to handle whatever might happen, all because they spent hours in a machine that convinced them they were flying when they were actually sitting in a building, never more than a few feet off the ground. Here's something that sounds like it should be straightforward, but actually becomes quite complicated. Measuring how fast an airplane is flying. You might think speed is speed. Just measure how many miles you cover in an hour and you're done. But at high altitudes, where the air is thin and temperature varies dramatically, the straightforward approach doesn't tell you what you actually need to know about the aircraft's performance and safety margins. The speed of sound isn't constant. It changes with temperature. In warm air, sound travels faster. In cold air, it travels slower. At cruising altitude, where temperatures can be 70 degrees below 0 Fahrenheit, sound travels significantly slower than it does on a warm day at sea level. And since one of the critical limitations on aircraft speed is approaching the speed of sound, that's where compressibility effects and shock waves start causing problems. Pilots need to know how fast they're going relative to the local speed of sound, not just in absolute terms. That's why high-altitude aircraft measure speed in Mach numbers, the ratio of the aircraft's speed to the speed of sound in the surrounding air. Mach 0.85 means the plane is travelling at 85% of the speed of sound, whatever that speed happens to be at the current altitude and temperature. This tells the pilots what they actually need to know, how close they are to the compressibility regime. Yeah, how much margin they have before aerodynamic effects become problematic. But there's another complication. The airspeed indicator in the cockpit doesn't measure absolute speed through the air either. It measures dynamic pressure, the force exerted by the air hitting the aircraft. In thin air at high altitude, the same dynamic pressure corresponds to a higher true airspeed. So the indicated airspeed might read 250 knots, but the aircraft could actually be moving through the air at 450 knots true airspeed. Both numbers are correct, they're just measuring different things. Indicated airspeed tells you about the aerodynamic forces on the aircraft, how close you are to stalling, how much lift the wings are generating. True airspeed tells you how fast you're actually covering ground, more or less, not accounting for winds. And then there's ground speed, which factors in winds. You could be flying at 500 knots true airspeed but experiencing a 100 knot headwind, making your ground speed only 400 knots. That's what matters for navigation, how quickly you're actually getting where you're going. So a simple question, how fast is the plane flying, has at least 3 different answers: indicated airspeed, true airspeed, and ground speed. And at high altitudes, Mach number becomes more relevant than any of them for understanding where you are in the aircraft's performance envelope. Modern cockpits display all of these, each one useful for different purposes, each one measuring speed in a way that's relevant to a different aspect of flight. It's a reminder that even simple concepts become layered with nuance when you're operating in extreme environments. For speed is relative to the air, relative to the speed of sound, relative to the ground. The number that matters depends on what question you're trying to answer. There are experimental aircraft designs that challenge one of the most fundamental assumptions about what an airplane must look like, that it needs a vertical tail. For more than a century, nearly every airplane built has followed the same basic configuration. Wings, fuselage, horizontal stabilizer for pitch control, and a vertical stabilizer, the tail fin, for directional stability and yaw control. But some cutting-edge designs are asking, what if we could eliminate that vertical tail entirely? These tailless designs aren't entirely new. Flying wings and delta-winged aircraft have existed for decades. But modern approaches are getting more sophisticated, using a combination of differential thrust, varying power between left and right engines, and advanced wing control surfaces to maintain directional stability. Computer flight control systems can make thousands of tiny adjustments per second, using engine power and wing surfaces to do the job that a traditional rudder and vertical stabilizer would handle. The advantages of eliminating the vertical tail are significant. Tails create drag. Their surfaces sticking into the airflow that contribute nothing to lift, existing purely for stability and control. Remove them, and you reduce weight, reduce drag, improve fuel efficiency. For military aircraft, there's another benefit: radar cross-section. That vertical tail is highly visible to radar, making the aircraft easier to detect. A tailless design can be much stealthier, harder to track. But the challenges are real too. Directional stability becomes entirely dependent on active control systems. Lose electrical power or computer control, and the aircraft becomes difficult or impossible to manage. Traditional aircraft with vertical tails have inherent stability. They naturally want to fly straight because of the weather vane effect of that tail surface. Tailless designs have to create that stability artificially, constantly, through active corrections. And there's something philosophically interesting about this shift. For over 100 years since the Wright brothers, we've built aircraft with a certain configuration because it worked reliably, predictably. The vertical tail became part of the definition of what an airplane looks like. But as computer systems become more capable, as we trust active stability control more completely, we can start questioning those assumptions. Maybe an airplane doesn't need a vertical tail. Maybe we can achieve the same results through computation and active control, accepting the dependency on complex systems in exchange for efficiency gains and performance improvements. These tailless aircraft represent a reimagining of fundamental aircraft design, not just incremental improvements to existing concepts, but a genuine rethinking of what an airplane must be. They challenge assumptions held for over a century, asking whether the basic configuration we've relied on is truly necessary, or just one solution among many possible approaches. And as computing power and control system continue to improve, these alternative designs become more feasible, more practical, potentially the future of how we build aircraft. The tail might not be necessary after all. We just needed computers smart enough and fast enough to compensate for its absence, creating stability through active control rather than passive design. It's a different philosophy of flight, and it's becoming reality in laboratories and test facilities, slowly proving that even the most fundamental features of aircraft design are negotiable if you're willing to rethink everything. Despite how routine flying feels today, despite how we board casually, scroll through our phones during taxi, doze off during cruise, there's something worth pausing on as we reach the end of this journey through aviation facts. You're travelling in a pressurised metal tube at over 500 miles per hour, more than 6 miles above the Earth's surface. Sustained by principles of physics that still inspire wonder, even in the engineers who design these machines. Every flight is an ongoing negotiation with the laws of nature, a controlled fall that became humanity's most reliable form of long-distance travel. Think about what's actually happening up there. You're in an environment that would kill you in seconds, air too thin to breathe, temperatures cold enough to freeze you solid, atmospheric pressure so low your blood would boil. But a few millimeters of aluminum or composite separate you from that hostility, and inside that shell you're comfortable. Reading, eating, sleeping, completely unaware of the extreme environment just beyond the window. Engines are burning thousands of gallons of fuel, generating power equivalent to hundreds of cars, and pushing against drag forces that would stop anything slower. Wings are flexing, systems are monitoring, computers are adjusting, all of it working together to keep you suspended in the sky, and it's so reliable, so routine, that we've stopped noticing the miracle of it. You can buy a ticket, show up at the airport, board a plane, and with statistical near certainty arrive safely at your destination hours later, and hundreds or thousands of miles away. The accident rate for commercial aviation is measured in events per 10 million flights. You're safer in the air than you are driving to the airport. That safety didn't happen by accident. It's the result of decades of refinement, countless lessons learned from failures, obsessive attention to every detail from tire pressure to fuel chemistry to cockpit layout. Every generation of aircraft is better than the last, more efficient, more reliable, safer, quieter, cleaner. The problems that seemed insurmountable to early aviation pioneers, metal fatigue, compressibility effects, high-altitude flight, intercontinental range, have all been solved, not perfectly but adequately, well enough that millions of people trust their lives to these solutions every single day. And new challenges emerge: sustainability, noise pollution, contrail effects on climate. Each one will be addressed, compromised with, engineered around, just like all the challenges that came before. So maybe as you drift off to sleep tonight, thinking about airplanes, you can hold two thoughts simultaneously: that flying is mundane, ordinary, routine, barely worth thinking about in our modern world, and also that flying is extraordinary, impossible, miraculous, a feat of engineering and physics and human ambition that would have seemed like pure fantasy just a few generations ago. Both things are true. We've made the impossible routine, and that might be the most remarkable achievement of all. And so we've drifted through 50 facts about airplanes, from those first 12 seconds above the sand at Kitty Hawk to modern aircraft that can circle the globe without stopping, from the microscopic cracks in fatigued metal to the vast distances crossed at speeds that outrun the sun. We've explored wings that bend like trees in wind, engines powerful enough to light small cities, pilots who age microseconds slower because of the speeds they travel. We've thought about the ordinary made extraordinary, the routine that required solving hundreds of impossible problems. Maybe what's most beautiful about aviation isn't any single fact, but the accumulation of them, the realization that every flight represents thousands of solved problems, millions of components working together, a century of continuous refinement and learning. Every time you board an airplane, you're trusting your life to this accumulated wisdom, this vast collaborative effort across generations of engineers and pilots and scientists, who each contributed small pieces to a system that, somehow, works reliably enough that we barely think about it anymore. The sky used to be a barrier, something that separated Earth from the unreachable above. Now it's a highway, a medium we move through as casually as we drive across town. That transformation happened one innovation at a time, one solved problem after another, until the impossible became so routine that we sometimes forget to be amazed by it. But tonight, maybe you can remember. The next time you fly, maybe you'll notice the wings flexing. Think about the air being compressed for you to breathe. Appreciate the quiet engineering victories that keep you safe and comfortable at 35,000 feet. Or maybe you'll just drift off to sleep, lulled by the steady drone of engines, secure in the knowledge that countless brilliant minds have worked to make this miracle mundane. Sleep well, sleepy learner. The airplanes will still be up there tomorrow, drawing their temporary lines across the sky, carrying people and dreams and possibilities from one distant place to another. And maybe that's exactly as it should be. The extraordinary becoming ordinary, the impossible becoming routine. Humanity learning to fly and then beautifully learning to take it for granted. Good night.